how the design work goes on in small hydropower plants, and we start with the diversion weir and the hydraulic canal and the desilting basin to begin with, and then we will proceed with the 4-bay tank, design of the 4-bay tank and penstock and so on. And as we already understand, we look at these things from a hydropower engineer's point of view. So, we will not go into do the civil engineer's work, but we will tell the civil engineer these are the sizes of the canal and other components that we are interested in. It will depend upon the rated flow rate, etc. All those decisions will be taken by the hydropower engineer. So, as we understand, these are the regular components of a small hydropower plant, which is usually a run of river scheme. So, we have the diversion weir here, where we divert water from the regular path where the water is flowing in the river into a canal in our case, but in a large hydropower plant it may be a tunnel. So, we take this canal along the canal to a convenient location where the 4-bay tank is located, from where the penstock begins. Today we will look at this location of the diversion weir and also the canal, how to size the canal and what should be the exact slope of the canal. It is generally about 1 to 1000, but exact value we can calculate depending upon our project parameters, that also we look at. So, these are the things that we look at, and also the 4-bay tank size, what should be the volume of the 4-bay tank for a given project. So, when locating the diversion weir, there are certain precautions we should take in selecting the location in the stream. So, we approximately know where it should be from the maps, etc., but we will decide it after visiting the site and having looked at the width of the river and also the nature of the river banks, whether they are rocky and good for connecting the diversion weir, or whether they may be loose soil. In that case, we will have to either shift it a little bit up and down to go for a better location. So, the purpose of the weir is to divert water through the water intake into the canal with minimum impact on the water stream. We will not make a big dam in like a large hydropower plant. We will make a small dam. I have put some pictures here. You can see here. This is one of the projects I manage. So, we just use the natural features of the river without breaking them. There was a rock here. So, we used the rock and anchored our diversion weir into it. You can see. So, and our canal intake is here. So, the water comes into our project from here, otherwise the river was flowing like this in this way, right. So, diversion weir is just to divert water. This is another project that we did, and it is right on the top of a rock. So, that is it is easy to connect. So, it will not wear out and erode later on. So, if the weir is too tall, the backwater curve will be raised and the lands upstream will get inundated or flooded, which we do not want. When the weir is located at a narrow place of the river, the cost will go down. So, we must look at all these things when deciding the final location. If the weir can be connected to a large rock on the river bank, the weir is safe and strong. So, because these things have to last maybe over 20, 30, even 40, 50 years. So, there will be erosion and other things in the river beds. Therefore, we should look at these things and use natural features as much as possible for the stable construction of these components. So, the mouth of the water intake should be placed in such a way that minimum amount of debris, sand, etc., flow into the river can enter it, as well as the logs and other large floating objects will not damage the water intake. You know, now if you keep the mouth just facing the water flow in the river, all the sand and things will come and enter your canal. Therefore, we would like to keep it in a side way. So, the water can smoothly enter, but not the floating objects. Floating objects will go directly in the river, but rather we will keep the mouth in such a way, the intake mouth in such a way, as little as possible this strange materials and sand can enter our mouth, our intake mouth. If the water intake at the inside of a bend of the river, more debris and sand can enter the water intake as the water flow rate near the inside of the bend is slower. I think probably if you have a bend in the river, right, bend in the river, we know that now if the river flows like this, now the water in the outside periphery has to go faster because the length is more and the inside is slower because the distance is less. Then what happens is sand and other things accumulates here because the water speed is less here, and water speed high here, there will be no accumulation here. Therefore, if you keep your water intake mouth here, then more sand can enter because the water flow rate is slower, things get accumulated and part will enter your intake. If you keep it here, it will not happen, right. Therefore, all these precautions we should take, right. If the water intake can be shadowed behind a naturally located rock, the protection of it can be ensured against heavy floating objects. You know, sometimes in a river even trees can float in flood season, big logs can come. If they can come and hit your water intake, it will be damaged. It will be damaged. You can see here, this is the water intake we had in one project. So, you can see that we have put a coarse trash rack here, so that not big pieces of logs etc. can enter our intake. But of course, leaves and other things will come in, but we have the trash racks afterwards to remove them, right. But here you can have put a, so there is a rock here, right. Therefore, if there are any logs and other things come in, they will not, most of them will not enter here, they will go in the river, right. So, we should look at all these things in relocating the mouth of the intake structure. Another important aspect to be considered when locating the weir is the stability of the river bed at the weir location. So, if that is not rocky, then it will be on soil. So, you will have to have a foundation like thing. But you know, we are looking at a structure with a lifetime of 20, 30, 40 years, as I said earlier. But the river bed can erode over the years. I have put a picture here, it has happened. You can see original level has been this, but now you can say about a meter has been eroded over the years, right. So, it had to be now this has to be additionally supported with concrete work later on, right. So, these things cannot sometimes be avoided, but as much as possible we should look at these things when it happens. Our weir will not be washed away or pushed away. In ancient times, wooden planks, rubble masonry work as well as soil bunds have been used to construct weirs. In the olden days, I think you may have also seen wooden planks etc. used for water diversion weirs, right. But nowadays, we prefer always to use concrete dams in the small hydropower industry. In building weirs, therefore, maximum utilization should be made of the natural features of the river, and thereby the cost of construction can be minimized. And the power, we call the canal sometimes the power conduit, because it in a small hydropower project, it brings the power, water with power. So, we sometimes use the word power conduit, or rather sometimes we say, mostly we say the canal. The main aim of using the canal or power conduit in a small hydropower project is to reduce the length of expensive penstock pipes. There is no technical hindrance to use the penstock pipe from the weir down to the powerhouse, except that there will be increased losses in the pipe, what we call the head losses. Typically, the canals are built with a very little slope, such as 1 to 1000, and therefore, the head loss is minimum. Thus, the canal is routed very parallel to a contour line through the water intake. We can see earlier also I showed you that this is the canal, which is going almost parallel to a contour line. Contour lines are lines showing the equal height. So, for a 1 kilometer canal, drop will be approximately about 1 meter, So, if you look at the contour lines with a contour map with height 20 meter difference, so you can see 1 meter will be very small amount, right. So, it is we can say almost canal is going parallel to the nearest contour line. Here is a canal we constructed for a project. This is for one of the projects that I manage. You can see there can be bends, etc., but you route it at the periphery of a hill. You can see we have a cut here, and then on that we will construct it looking at the stability of the soil, etc. Here you can see it is a reinforced concrete canal. Canals are built in number of ways, similar to many irrigation canals in many places. It can be simply dug into the soil. I think in India also you have seen in the old irrigation schemes, canals are just dug into the soil. So, they are soil canals, right. But their flow rates are very small, in that otherwise the banks will be eroded. But in hydropower projects we need a sufficient water rate to come. Q has to be sufficiently large. Therefore, we do not want erosion to damage it over the years and make trouble. The same can be further strengthened by cement rubble masonry work. But nowadays concrete canals are built usually above the ground level, are very common and preferred in small hydropower projects. So, the power projects that we are talking are projects to be supplying to a grid stable power and through a PPA. So, they have to be well constructed. Therefore, we do not want to have trouble in bringing sand and other things in a canal into a powerhouse and to the penstock. And therefore, we always have concrete canals, rectangular concrete canals now constructed above ground level. Even a fiber reinforced plastic FRP or a steel low pressure pipe can also be used instead of a canal. When the construction of a canal is problematic due to land features, complete canal or part of a canal can be through by pipes, either concrete pipes or these are FRP pipes, fiber reinforced plastic pipes. So, in some of the projects in Sri Lanka, we have used this kind of low pressure pipes and also concrete pipes sometimes, which are sometimes buried or above ground. We can, depending upon the location, we can use them. The cross section of a canal can be numerous shapes, and the rectangular and trapezoidal cross sections are some examples. Canals with rectangular cross sections, usually built above the ground level, are very common in small hydropower plants built in Sri Lanka. The purpose of the canal is to fetch water from the weir to the forebay tank at the required water flow rate. When the speed of water in the canal is high, the cross section of the get reduced and is more economical. However, the speed of the water flow cannot be increased beyond the limitations posed by the canal wall material, as otherwise excessive erosion will take place. For concrete canals, a maximum water speed of 1.6 meters per second is allowed to avoid wall erosion, right. So, you will not believe that after 5 years, 10 years operation, you will see entire cement plaster is gone, and sometimes even up to the steel reinforcement erosion can happen if the water speed is too much. Then you will have to replaster it, stop in the power plant for months. Therefore, it is necessary to keep the speed to maximum of 1.6 meters per second, when the erosion will be minimum. Here are some shapes. So, usually nowadays we use rectangular concrete canals. With the water level filled to up to a certain level, and this is okay. We will come to that. This trapezoidal cross section is more suitable when it is constructed. This is above ground level. So, when it is constructed below ground level, it is more economical, right. So, this is going above ground level, this is going below ground level, but we prefer always this. So, in order to decide the cross section area of a canal, following are considered, right. So, we now as a hydropower engineer, we must decide what should be the cross sectional area of the canal, right. So, the things that we used for this decision are allowable water speed in the canal, roughness of the inner surface of it, shape of the cross section. If the water speed is too high, the walls of the canal get eroded. To get the high water speed, a higher slope is required, and this will increase the head loss. At the same time, if the water speed is too low, silt and other debris will get accumulated at the bottom of the canal and will eventually block it. So, water speed also cannot be too slow. When water speed is too slow, then sand and other things will sit in the bottom. They will not move with the speed is too small. Therefore, we must have optimum speed. For water, therefore, water carrying silt, the minimum speed should be at least 0.3 meters per second. And if the water carries sand particles, the speed of water in canal should be at least 0.5 meters per second to avoid sand accumulation in the canal bottom. For concrete canals, by keeping the maximum speed to 1.6 meters per second, the erosion of the concrete walls can be avoided. Then we calculate a parameter called hydraulic radius. So, this is not a physical parameter, but this is this we use for in sizing the canal to increase the efficiency of the canal. So, this is something defined as water cross sectional area divided by wetted perimeter. So, here I have shown a sample, you can see water is up to this level. So, the water cross sectional area is this, and the wetted perimeter is this up to here, this length, wetted perimeter, where the water touches the canal area. And then what is the canal height above the water level, we call it freeboard. Right. So, the hydraulic radius implies that for a given water cross section, less area of contact, high hydraulic radius implies that for a given water cross section, less area of contact between water and the canal and consequently less friction. You can see if the hydraulic radius high means for a water cross sectional area, for a given cross sectional area, wetted perimeter is minimum, right. High radius, hydraulic radius means wetted perimeter is small for a given cross section, right. When it is small, what does it mean? The friction offered by the canal to water flow is minimum when wetted perimeter is so. So, therefore, we prefer higher hydraulic radius, right. Therefore, such canals require less slope to achieve the desired water flow rate. If the friction is more, you need more slope to be sacrificed, right. The slope you sacrifice because the canal slope cannot be finally pressurizing the water into the turbine. Therefore, we are losing that head. Therefore, we would like to keep it as small as possible, slope of the canal. So, in order to do that, the friction between the water flow and the wall should be less, right. So, here are some hydraulic radius values for different cross sectional areas. Semicircular 0.4 into square root of cross sectional area, water cross sectional area. Trapezoidal using this formula, where the theta is the angle between the wall and the horizontal surface, and rectangular 0.35 into square root of A, the water cross section area. This parameter is useful for us to size in the canal, right. So, the cross sectional area and the slope of the canal for a small hydropower project can be estimated by following the following steps. First step is to calculate the cross sectional area taking the required rated flow rate Q and the allowable maximum water speed for canal. The decision of Q we will separately consider in a separate lecture, how to decide the rated flow rate QR, that is required for sizing all these components. So, for the time being assume we know QR, rated flow, right, and the V we can say what is the allowable maximum speed. If it is concrete, we can say 1.6 is the maximum, let us say we select 1.5 meters per second, right. Therefore, we can calculate what is the required water cross sectional area, right. Decide a suitable cross sectional shape, whether it is rectangular or semicircular or trapezoidal. Usually, we go for rectangular cross section. Once the hydraulic radius is known, determine the optimum canal dimensions from the table below. You can see. So, suppose we decide to get it as usual rectangular cross section. Therefore, we know for a rectangular cross section it is 0.35 into square root of A. These things you can calculate using the definition, using simple mathematics, right. So, it is 0.35 into square root of A, right. So, A can be calculated. So, suppose Q rated is 2 cubic meters per second, which decision we will make in some other lecture. 2 divided by say 1.5 square meters, right. Now, then hydraulic radius will be square root of A is equal to 2 divided by 1.5, right. And so, we can calculate what is hydraulic radius. I put some typical values, for depending upon your project you put the actual value, right. So, once you know the I first refer to this table, right. Once you know the hydraulic radius, these are the optimum parameters for the different canals. So, if it is rectangular, take the depth as 2r and width as 4r. For it should be trapezoidal sin theta, not here, right, 4r. So, if it is say r is say 1.2 meter, then your canal dimensions will be 4r and 2r, 2r height, 4r width, right. So, it is easy. So, all depends upon your hydraulic radius, which we select to make the canal more efficient, right. We select to make the canal more efficient. And then you have to know what is the freeboard, that is how much height should be there above the water level, freeboard, that we decide based on the you know that if you do not have the freeboard, what happens? Water will overflow everywhere, right. Water will overflow at unintended places, causing erosion. You can see a sample here. When we were commissioning one project, there was the canal had a problem, its freeboard was not enough at one location. Therefore, water started to overflow, right. Luckily, there were rocky surface here. So, the bank erosion did not take place, but otherwise it is dangerous. Therefore, we must have water to overflow if necessary at intended places. So, we have here made a water overflow canal. So, that is nicely made. You can see water can flow back to the river without causing erosion to the hillside, right. But here it is dangerous, it can erode the bank and the total structure can come down, right. Therefore, what we do is, you can see here, this is the canal, right. Here is the canal, right, and we assume due to some reason the canal get fully blocked, right, maybe falling of some soil or something, if canal get fully blocked, now the water level become horizontal like this and start to overflow here, right. Water will accumulated, fill the canal, this is the freeboard, right. Earlier water was flowing like this, right, but now because of the block, water level has gone up at this location and is about to overflow here, right. But now if we had the opening slot here, then the water will not overflow here, but water will overflow at the intended place, right. So, therefore, we must have these overflow canals located intentionally. Therefore, our slope should be right equal to freeboard divided by the length between this overflow canal. You must have a overflow canal at length L, right. In that case, water cannot overflow at unhindered places, but here, right. Therefore, the maximum distance between overflow canals will be, you can put the other way, L is equal to freeboard divided by the slope of your canal, right. So, you should decide the freeboard looking at the number of overflow canals you can have in your project, because overflow canals also expensive, this has to have some money, right. So, if you keep very small freeboard, you will need more number of overflow canals, right. You will need more number of overflow canals. So, you will have to spend money on that, but if you keep high freeboard, your canal will be bit expensive, right, because of the concrete. You have to have a that level above the normal water level, right. Therefore, canal will be expensive to construct. So, you have to have a balance. So, one of the better ways is, look at the natural features of your project. I will go back a little. You can see here, when you have your overflow canal, if there is a natural river or natural stream somewhere, so you can make them overflow canals. You can let your canal to overflow at such locations. Therefore, you do not have to build a new overflow canal. You can use the existing crossing, river or the stream crossing, instead of building a new one, fully artificial one, right. So, you must look at the natural things available in the route you have selected for the canal, whether there are already any streams you are crossing. Then let design your canal to overflow at such locations, right, minimizing the necessary cost for the overflow canals, right. And you can increase or decrease the number of overflow canals by increasing or decreasing the freeboard. So, whether to construct an additional overflow canal or bear the cost of the increased freeboard. So, that is a question to be answered. So, that we do in the best interest, after utilizing all the available streams which are crossing the canal path. We will decide whether we will use few number of canals, overflow canals, or we will use we will decide to increase the freeboard a little bit more, right, decreasing the number of overflow canals required. And here is a formula, right, this is Manning's formula to calculate the slope of your canal. So, slope of your canal is given by N V divided by R to the power 2/3, right. N is roughness coefficient of your material of the canal, right, and V is the speed of water, R is the hydraulic radius you have calculated. You can see N is 0.014, needs cement plaster. If we have plastered the concrete, right, it will be 0.01. These are from civil engineering handbooks. N is equal to 0.015 for concrete. That is, if you have not plastered the concrete, just smooth finishing only, then it is a little bit rougher concrete surface. But if you can plaster it with cement sand mortar, then it will be smoother. So, this roughness coefficient is going down. So, I earlier said slope is about 1 to 1000, but this formula will give you, but near to this, but not exactly 1 to 1000, maybe 0.7 to 1000 or something quite closer. Roughly we say it is 1 to 1000, but the exact value you must calculate using this formula, right. slope, and depending upon the slope, freeboard and other things. Now, we come to the desilting basin. What is the desilting basin? A trap to remove sand and other particles, suspended particles that are flowing in the canal with the canal water. We do not want it to go and enter the penstock, so that it can damage the turbine blades by erosion and other things, impacts, right. If silt and sand enters the turbine through the penstock, runners can get damaged by erosion. Therefore, depending upon the amount of silt in the river and the length of the canal, etc., one or several desilting basins are used to remove silt from the canal. Final desilting basin will be built integral with the forebay tank. So, just before the water entry to the penstock, we must have a desilting basin, because if by any chance any sand comes and enter the penstock, that can damage the turbine. Therefore, we must have one desilting basin at the entry to the penstock, but we can have a couple of more if the canal length is quite high. Maybe if it is a 1 kilometer canal, maybe you can have one at the very entry, one in the middle, one at the end, and means at the forebay tank. The principle used in desilting basin is reducing the speed of water flow by widening the canal and thereby allowing sufficient time for the heavy particles to get trapped in the deep bottom. So, these values will come later on. I will just go to the next slide to show you the arrangement. You can see. So, here is a water flow cross section, sectional view of the canal. You can see that water comes here. So, this is the plan view. So, the water comes regularly in the canal width is W, right. And now, we construct a desilting basin. Desilting basin is we widen the canal, so that the water speed will go down. When the water speed goes down, the particles can settle, right. So, idea is now the speed is low, therefore, particle begins to settle down, and the idea is, so we have a bigger bottom, right, trap water bottom trap here. So, normal canal bottom is here. So, we have deepened it. So, that the idea is particle will trap here and will be collected in the trap rather than going into the other side. Why it is settling? Because now the water speed has come down, right, water speed has come down, therefore, it start to settle at the settling speed of V naught. I think we have studied in these things in that in A level physics and all that, right, settling of particles because of the the parameters of the fluid parameters, right. So, but we know that the water flow rate is, if the water flow rate is Q, then Q is equal to V into the area, right. So, area. So, here in this section area is width into height h, right. But here area is, this is a rectangular area, say A1, this is A2. So, A2 will be V1 into W1, right. But A1, right. So, sorry, not V, W1 into H, I made a mistake, W1 into H, right. So, we know that the Q has to be the same, water flow rate cubic meters per second cannot change, because if it changes, then water has to go somewhere else, right. Therefore, in both places Q has to be same. Therefore, this Q is equal to V into A1, right, and also Q is equal to V1 into A2, right. So, V into A1 should be equals to V1 into A2, because the Q is the same, right. Therefore, we can put these numbers into it and then show that V into W is equal to V1 into W1. I think you can put the numbers here and get this, right. But in order to trap the particle, this is the important parameter, right. Your settling time when it particle comes to here to settle distance of h, right, this settle distance of h, the time taken is speed into, right, the distance divided by time is equal to distance divided by the speed, right, speed, right, distance divided by speed. Here the distance is h, right, h, and the speed is v naught. So, the time t naught is h divided by v naught, right, and so it should be less than time taken to cross the canal, cross the tank, that is travel distance of L. So, L divided by V1, V1 is the speed in the water speed in the horizontal direction, right. So, it should be T naught should be less than T1, T1 is the time required to cross this trap, right. So, by the time it comes here, it must have settled below this level. So, it will be trapped here, right, it will be trapped here. So, then you can show that using all these equations, LW1 is should be more than VWH divided by V naught. If you put these numbers into this, it will, you can show this, right. To save our time, I will not go into this, simplify this, but if you have any questions, we can look at it later on. So, then we can size it, size the tank, we can select numbers for W1 and L to satisfy this condition, right, satisfy this condition. So, that, and also we will look at the location, whether we can't increase sometimes W1 too much if the location does not permit, because we are constructing this at the edge of a hill. So, sometimes you can't have too big W1, then in that case you can increase L, capital L. So, whether the numbers we will look at, as long as this condition is satisfied, particles will be trapped, right, particles will be trapped. Probably you will have some, if you did get all the answers here, maybe at a Q&A session we can look at how the numbers are worked out. I am sure with your advanced level knowledge you can easily get these things, right. So, here are some typical values for V naught, by they find these things by lab experiments. For particles of diameter 0.1 millimeter, V naught can be 1 meter per minute, that is a settling speed, right. For particles of diameter 0.8 millimeter, 5 meters per minute. So, you can use typical numbers, you can get these things from civil engineering handbooks, right. So, through lab experiments they have found these numbers, right. So, accordingly dimensions L and W can be determined. Typically, V1 is about 0.3 to 0.5 meters per second, right. Here are some samples under construction, desilting basins, you can see. So, this is the canal bringing water, right, and we have widened the canal as we said earlier, right, and also made the bottom here, deepen the bottom, so that the sand particles can be trapped onto it, right, and we keep a side opening here, right. We can keep an opening here, time to time you open the valve to remove the accumulated silt, right, maybe once a week, once a month, depending upon the silt situation, there is an opening here, somebody goes and open the valve, so that all the sand and silt etc. accumulated will be going out, right, otherwise it will be getting filled. Here you can see they are keeping a opening, putting a opening here to put a valve here, so that accumulated sand can be removed, right. So, this is under construction. So, all these walls will be concreted, right, and the canal will continue on the other side. Here you can see people are working on this trap, right. Then we said that we need to have a trash rack, right. We need to have a trash rack. Why we have a trash rack? To stop any floating debris like leaves, logs, even animals, right, going into the penstock and finally going into the needle valve or wicket gates. We will discuss in these things under another topic, what is a needle valve, what is a wicket gate, etc. But they can be blocked by this big floating object if they go, even animals, fish or anybody. Therefore, we must have a mesh. Trash rack is a mesh, right, to avoid any floating object. Now, the sand and other particles which are settling, we have removed with the settling basin, but the settling basin will not remove floating debris, floating objects. Therefore, we must have a trash rack, right. So, when open canals flow through forest areas, leaves and twigs as well as small animals who try to drink water from the canal fall into the flowing water. The rivers also carry a substantial amount of floating debris. Therefore, it is necessary to prevent them from entering the penstock to avoid nozzles, wicket gates getting clogged. Trash racks are located at several places of the canal for this purpose. At the water intake to canal, a coarse trash rack, as we looked at earlier, is used to prevent relatively large floating objects entering the canal. Usually at the water intake point to the forebay tank, there is a well graded trash rack in order to make sure if any floating object enters the penstock, it leaves the nozzles without getting trapped inside the opening of the trash rack. So, the final criteria is, if your final jet, water jet opening diameter is the opening of your jet, right, opening of your jet, say its diameter is D, right. If the diameter is D, you make sure your trash rack slot size is less than half of it, right, half the D. Then what happens? If something enters, it can go through the nozzle and will not block the nozzle. If it is more than half the diameter, then it can go and block, right. So, we will make sure that if something goes inside, it can leave the nozzle rather than blocking it, right. Therefore, we will make sure our trash rack mesh sizes so this size, mesh size should be less than half the diameter of the nozzle. That is, if some particle goes in, it can leave rather than blocking the nozzle, right, rather than blocking the nozzle. Here is an example, you can see trash rack sizes. So, that all the leaves and logs and etc. will be accumulated, and this is an automated trash rack, but you can see that sometimes it is economical in our countries to employ somebody and remove the trash. You can see somebody, he is now fixing it, or he is removing some trapped leaves, etc. You can see it can be opened, trash rack is in parts here, right, it can be opened and then it can be lowered to close it. So, the water will be filtered when it flows inside into the forebay tank, right. Now, here they have lifted it to go inside or something, right. So, somebody will stand here with a stick later on to remove anything getting collected here with the flowing water, right. Here this is done by automatic trash rack here. So, now we come to the canal will bring water to the forebay tank, right. Canal will bring now water to the forebay tank, and from the forebay tank begins the trash rack. So, we have begins the penstock. The penstock will begin here and then go down to the powerhouse, right. So, this is our forebay tank, right. So, canal brings water into forebay tank. at rate of cubic meters per second, right. So, why we need a forebay tank? Why can't connect directly the penstock to the canal, right? It is a question. So, because forebay tank will cost you money, but the problem is now when you are synchronizing the generator to the grid, right, or in under transient conditions, your the required flow rate will be varying a lot at the powerhouse center with the control center. Then what will happen? Then the canal water level will try to go up and down, because you are sucking more water than coming in, right. Therefore, the canal water level can be going up and down. We want to avoid that. Therefore, we have, if we have the big tank here, water level will not be very much affected under transient water conditions. Therefore, we have a sufficient collection of water here in a tank called forebay tank to avoid under transient conditions the water level going up and down significantly. Of course, it will go up and down a little, but it will not go significantly, because we have a water collection here, right. So, the main purpose of the forebay tank are to act as the final desilting basin that we discussed earlier. The final desilting basin will be with the forebay tank to stock sufficient water, so that it is easier to handle any transient water demands by the plant. For this water sufficient to operate the plant for full load for about 2 to 3 minutes is stored in the forebay tank. So, this is by experience, right. By experience we know, if we have about 2 to 3 minutes water requirement, right, in the forebay tank, then water level going up and down is very small, and then you can avoid any transient water level decreasing, and to act as the final trash rack, right. So, these are the three functions of the forebay tank, and the volume is decided by this requirement. So, if the water flow rate is say 2 cubic meters per second, 2 cubic meters per second, then you have forebay tank volume to be as least 2 into say 3 minute, right, 180, which is equal to 360 cubic meters, 360 cubic meters. So, you can have the length, width and height decided by the various requirements, like you have to have the desilting basin, you will have to have the trash rack, then you will need to look at the available space in the ground by the location features of the location. So, by looking at all these things, you make sure that total volume is 360, but the width, depth and height, all these things you can decide to be having this volume, right. So, you look at the space available in the ground, whether we can have length like this or width like this. So, therefore, depending upon the requirement of the physical features of the ground, you decide the total the individual parameters, but the total volume should be about 360 cubic meters, right. That is the only criteria, but other things you decide depending upon the available space, etc. Here are some examples. You can see this is you can see what a big canal bringing it and enters here. So, we must have the trash rack here, right. This is under construction, and then this is where the penstock is connected on the other side, right, to the penstock. So, they are just finishing it, right, connecting it, and then you have to concrete it and do other things required for that. Sometimes we will put some concrete slabs here, right, so that people can easily walk and inspect these things. So, the final part may be closed. Okay. So, I end the first discussion here. Stop now. Any questions you want to ask?
Sir, in the previous slide, just the previous slide, sir, first figure, that is the penstock.
Yes,
This one, the
penstock getting
penstock.
connected to the forebay tank.
And that wall, behind that wall, it is the
This surface of the forebay tank
forebay
from
tank.
the other side,
Okay.
right.
And at the face of the forebay tank, we have this thrash rack.
Yes, the trash rack is here,
Okay.
but
So it is just little bit above the ground, na?
no, not the water flows here and enters here, maybe water level is up to here. So, the trash rack will be here. I think I should have drawn like this. It is facing the water flow. So, water has to go through the trash rack, so that the trash will be collected. It is a mesh, right, and this is the others from this side. So, the penstock is connected to the bottom side of the forebay tank, right.
So this is picture from which place?
This is from one site we did at a place called Pattnaik in Sri Lanka. I will show you some more pictures at the later on, some other features of the construction site.
Thank
This
you,
is a
sir.
4 megawatt one, this is a 4 megawatt plant. Having Pelton turbines, we will go through the turbine types etc. later on in a different discussion. Right.
Okay, thank you, sir.
Okay. So, we will stop there for the first part of the discussion. Thank you. Recording is stopped, no? Yeah. So, we will take a break of about 15 minutes and then start again. study, development of a flow duration curve and use of flow duration curve to determine the rated flow of the plant, because rated flow is required in sizing the plant, both canal and penstock, 4-bay tank, and all these component size will be determined by the requirement of the size of the rated flow. So, rated flow is an important parameter and it is decided based on the water availability in the river, flow rate in the available in the river. So, as usual this is our structure, our way of configuring a small hydropower plant. So, we have to know what will be the water flow rate that we can use from the river, cubic meters per second, that we can use in the small hydropower scheme, because our power generation depends upon Q, rho, G, H. H is a parameter depending upon the water height from the turbine level, and Q is the water that is coming into the canal, coming into our project, right. So, that now we are discussing how to determine Q for a given project, right. But before going into that, I would like to show you how to obtain this relationship of the power equation, because that is also important in this exercise, right. So, here you can see, so we are looking at that water carrying a potential energy in the 4-bay tank, this canal brings water here and we have the penstock here and we have the turbine here, and water jet goes and hit it, right, and rotate it. And so, our head is the top water level here and to the jet level in a high head project, right, and water flow rate is water that is flowing in the penstock, cubic meters per second, H is in meters, right. So, the potential energy here is, we know, mgh, right, mgh, that is the energy that it carries, as we know from the fundamental equations. E equals energy stored in the water is mgh, and we know the power is dE by dt, right, dE by dt. So, if you make dE by dt of mgh, G and H being constant, it is dm by dt into gh, right. dm by dt is mass flow rate of water, right, mass flow rate of water, dm by dt, which is equal to q into rho. I have used the simple q here, q into rho. You can see the unit, q is in cubic meters per second, rho is in kilograms per cubic meter. So, cubic meters will cancel, it is kilograms per second, right, kilograms per second is dm by dt, right, mass flow rate, right. So, you just replace dm by dt with q rho, then you come to this equation, P equals q rho gh, but at each energy transition there is a loss. To accommodate that, we introduce this efficiency term, because ideally you cannot transfer all the potential energy to kinetic energy in the turbine, right. So, it will be q rho gh multiplied by a efficiency factor, because otherwise 100% transfer is not possible, right. So, the overall efficiency is penstock efficiency, turbine efficiency, generator efficiency, transformer efficiency and transmission line efficiency all together, if you take the entire project, right, entire project. So, therefore, this is the final equation for hydropower generation, whether it is a small hydropower project or large hydropower project or pico hydropower project, same equation will apply, right, same equation will apply. Now, if you look at Q, it will be varying. Q is the water flow rate in the river, right, which can be diverted into our canal. you can see it can go up high, maybe 5 cubic meters per second, or it can be low, say 0.5 cubic meters per second, or in between, that we can't expect river to have constant flow, right, because it depends upon the upstream conditions in your catchment area. When it is raining, maybe it is maximum flow, and now it is 1 week, 2 weeks no rains. So, the flow rate will go down, and in the dry season it will be very small. So, this is time, days of the year, right, maybe 365 days here for 1 year, how the change is happening. So, this is a time series. So, this is a time series. So, where shall we say our plant be designed for? Rated flow here, or rated flow here, or rated flow here. I will call it QR1, QR2, QR3, right. So, how can we decide? If we use QR1, which is a high value, only during this period, and during this period your plant can run on full load, because rated flow is available only during those small periods, right. And if you select QR2, you can run a longer time at the rated capacity. See, the number of days your plant can run on rated capacity is more. If you use QR3, right, then much longer period you can run your plant on full load, because your plant full load will be efficiency into Q rated rho G H. H will be a constant almost, right, and so the QR will decide the plant capacity. Whether you call it here it may be a 4 megawatt plant, this may be a 3 megawatt plant, this may be a 2 megawatt plant, right. So, the smaller you select your rated flow, smaller will be your plant capacity, but the duration you can operate will be longer, right, duration you can operate will be longer. Therefore, which one we can decide, that is a question, right. So, to answer that question, we must convert this to a flow duration chart, right, flow duration chart. So, we will come to that, right, we will come to that. Now, we have come to now we have done a lot of studies and we are convinced that there is a good project. Therefore, this is right time to employ a professional hydrologist, right, professional hydrologist into our estimation, right. So, now what we do is we will show a professional hydrologist. We are going to do a hydropower project at this site. This is a water diversion location we have planned, and the catchment can be calculated in this area. Please show us how much water will be available at this location for diversion here at this point, the diversion, right, on a daily basis. That we are asking him do a study with his expert knowledge and tell us what will be the available Q, right, on a daily basis for 365 days, right. So, we will ask him this question. So, can you open the operators, can you open the PDF file? Excuse me, can the operators open the PDF file, please? Yes, okay. Maybe a site, maybe you can zoom it a little. So, this is for a project that we did in Sri Lanka. So, we have given this location, diversion location to a hydrologist. So, this is the report he submitted to us after his study. He took about 1 month for the studies with his expert knowledge. So, I will not read the entire report, but I will just read some initial lines. The purpose proposed project is across Lemastota, a tributary of Valley Oya, which is in turns the tributary of Walave Ganga. These are names of the rivers. The site can be reached from these places and so on. So, he says, and then he says objective of the study. Objective of the study, right. The objective of this study is to determine the long term flow regime of this catchment to assess the water availability from available hydrological data for hydropower development. So, that is the objective of the study. That is what we have given him, the assignment, right. This is a paid assignment. So, he will give us all these data. So, then he goes on hydrological data and so on. I will not waste time here, lot of time to read this report, but I will tell you what is the final outcome of study. He is using his expert knowledge and some mathematical models that he is used. He call is, you can see, I will read here, item 5, mathematical model. The correlation of daily rainfall and evaporation with the corresponding stream flow rates are interlinked in a mathematical model. In this study, NAM model developed by Danish Hydraulic Institution of Denmark was used to generate data. So, that is his expert area. So, he is using various models etc., to determine the daily average flow rates that can be expected depending upon the available data, right. So, he has used you can see now under for methodology, right. It says, therefore, model parameters were selected with experience in modeling similar catchments to generate stream flows for 30 years from long term rainfall available at Haputale from 1970. So, he has used data from 1970 to year 2000. We did this study in 2002, right. This report was generated somewhere there early 2000, right. So, he has used 30 years data, right, for this his model. Then he goes on his expert areas, data generation, flow duration data etc., right. And then he say low flow analysis. I am just showing you only the titles. Then the flood study, he says 50 years and 25 years flood study, because that is important for us to keep the powerhouse level. If the powerhouse we keep below the flood level, some bad year in a rainy year, our powerhouse can go underwater. Therefore, we ask him to give us what will be the maximum expected flood level at the powerhouse location. So, that also he include in his study, right. Then he goes on to say interpretations and various things, right. So, this is the name, this was done in 2004, right. Name is G.T. Dharmasen. He is a retired person from the irrigation department. So, they know all the historical data, they have the access to data and they have done all this modeling and all these things. So, they are the experts, right. You remember that I said some other time we do an approximate calculation, that is approximate, right. Not we can't, if you go with approximate calculation to raise a bank loan for the project, bank will ask who did the hydrological study. If the hydrologist is not acceptable to the bank, bank will say no, we can't give a loan, because your data is not dependable. So, you must have a reputed hydrologist to do the hydrological estimation. Then you can tell the bank we use such a person's predictions for our energy calculation. So, we can depend upon that, right. Okay. So, finally, with this report he will give a data set like this. Can the operators excuse me, can you operators start the flow duration, sorry, not the no flow data Excel file. Yeah. So, he will give us table like this. I will go to the bottom later. You can see it is flow data, units in cubic meters per second. Catchment area also he has put 17.9 square kilometers for this particular project. So, he gives for every month, he has started with October rather than January, October, November, December, then January, February, March up to September, right. And now he gives what can be the expected flow rate for each day of the month. October 1st, he says you can expect 3.354 cubic meters per second flow rate. we assume for the day it is constant, right. During the 24 hours we assume it to be constant, it might be slightly varying, but we assume it to be constant, right. So, and second 2.5, third 1.8, that is going down, right, and going down. On 10th of October we can expect increase, right, because maybe the next monsoon starts and so on, right. And so, this is depending upon the 30-year historical data that he has worked on, but based on that he says this is the best approximation, right, best approximation. And he goes like this for all the 31 days of the month, right, and for the other months, some month November and so on 30 days, right, and February 28 days and so on. So, he gives this chart. So, there ends his business, right, his work is over from here. So, we have used the hydrologist to get this table, and from this point onward this data we must use to determine what should be our rated flow rate and also how much energy we can annually generate. That is the business of a hydropower engineer. That is what we are learning from this course, right. How to use hydrologist data to go on and size our project, that is determine the Q flow rate, rated flow rate, and then each day how much energy we can generate, and also the capacity, what should be the plant capacity, etcetera. We should be able to calculate that, we will go through and see. Now, can you open the close this and open the flow duration curve slide. I hope I can work on this. Yeah, it seems I can. Here the same table, right, same table, right. Here there is an additional term here, 75% probable daily flow rate. So, he says these are his 70, the probability of these occurrences are 75% as per his model. You can see. So, I have done some calculations here. I have put zeros for the non-existing dates, so that the table is more calculable, and I have also calculated monthly average flow rate here. You can see average flow rate. So, I have averaged all the 30 days here column, you can see. Okay. Okay. Now we have to handle this data set, right. So, some statistical knowledge is required now, because we can't, they are all, right, different numbers depending upon the. So, we will put them into some ranges, right, pick them, put them into some ranges. Right. I have put, so let me insert column here, right. Here you can see. So, when I say can I draw something here? So, when I say 0 here, 0 and say 0.05 here, I mean it is 0.02 to 0.05, right. So, when I say 0.05 here, I really mean 0.00 to 0.05, right. So, this class, this range, I mean, I put a single number because otherwise I can't do calculations with this number if I put a figure like this. So, here it means 0.05 to 0.10, that class interval or range. right. So, that so you can see every number is a range I am putting it here, right. So, I just put the n number only, right, n number only, right. So, the size is 0.05, because I want to use this for calculation, that is why I put a single number here rather than the range, right. Okay. Now, I will want to count the number in this range 0.05 to 0.10, right, from that data table. How many points are here in that range, and put the number here, frequency column, right. You can see up to here there is no, but see there are 7 zeros, because there was number of months was not ending on 7 months. So, therefore, maybe on February 2 or 3 days were not there. So, altogether there are 7 months with zeros, which I have put purposely, right. Not hydrologists did not have zero flows on any date, any physical date, but I put zeros for the non-existing days, right. That is why the 7 zeros are there. Then in this range there are no any numbers, but 0.55, that means 0.50 to 0.55. They are count the maximum range is there, maximum number are there, right. 183 points are there in this table in that range, if you count it here, right. Right, if you count it here, right. So, likewise we can put to count all the numbers and put here, but to do it manually it is very difficult, right. You know, to count all the 365 data points and pick them up and put here is not possible. So, here we can use, therefore, there is a command in Excel called frequency command, right, frequency command. I do not know whether I can open can I open Google or something? I will type frequency command in Excel, right. Here you can see. So, frequency, data array and bins array, where data array is the range of your, I will just open it, maybe some of you are already familiar, right. So, I think you can go and study this, right, you can go and study this. How to do it I will tell you. I will just want to, I also have forgotten there is a sequence of sequence to press some buttons. Let me find out the Yeah, control shift enter, I must remember, control shift enter we have to press. Okay, I have forgotten it, that's I got it. Okay, here. Now the problem is how to count these data points in each class interval, right. That is a manually you can't do it. Therefore, we intend to use the frequency command. So, I have put, you can see here the frequency command, I do not know whether it is too small for you, right. Frequency command I have put it here. So, I will show you how to use it again, right. I will press freshly. Put the number. So, when I go to this cell, right, I will select the entire range here, range of class intervals I have selected. Can see there are class intervals I have selected up to 8.2, that is 8.15 to 8.2 also the last class interval. So, I will select that plus one more, right, plus one more, and then I will type start plus, right, I will type start typing frequency QUENCY and open bracket. Now, when as I open bracket, it gives a hint here, frequency, data array and bins array. Bins array are the class interval array, right. Data array is the data array that we have, data set that the hydrologist has given. So, I go to flow data one, give the data entire array here October 1st to September 30th, 31st. The 31st is not there, but theoretically we have put zeros for the 31st here. I will not give the average values here. This is the data array, right. This is the data array, entire data points in the data table that was given by the hydrologist, right. And then I will put a comma, and now it wants the bins array. Bins array are the this class interval column. Here class interval column, and now I will close the brackets, close the bracket. Now, we have to press 3 buttons together, control shift enter together, control shift enter, then it counts everything and put it here, right. Then it will count all the data points in that array data set and put them here, right. That is the easy way of picking up this, otherwise you can't do it manually. So, you can study frequency command separately and get this knowledge and do it as I said, right. So, then I have calculated cumulative frequency here, that is frequency plus the next one. So, up to here it is 7, then 7 plus 183, 190, 27 plus 190, 217 and so on. So, I have put all the values here, right. Because there are 372 data points, because we have put zeros for 7 days, 365 plus 7 days come, because we have put zeros for non-existing days, right. That is why it became 372. And then I have calculated probability of every frequency, right, that is frequency divided by 372, right. For this number of days, what is the probability, right, 183 divided by 372 here, right, E12 divided by 372, and likewise I have calculated, right, here. And then I have, because I want to get a certain shape of the graph, I have calculated 1 minus p and also percentage of that multiplied by 100, right. Now, I draw a graph between this last column and the first column, sorry, second column here, column C, right. I draw a graph between column C and column H, right. Then it happens to be a graph like this, flow, we call it a flow duration curve, right. So, for example, the vertical axis is flow rate, horizontal axis percentage time, right. So, for example, if you take any point here, right, for example, 1.5 cubic meters per second is available for, let us say 4, 8, maybe about 12% of the time of the year, right. If you take 0.5 cubic meters per second, flow rate is available for about 40, say 48% of the time of the year, right. So, rather than the time series curve, this is more useful for us, right. We know because in the time series curve, here you can see in the time series curve, you can see. So, to know how long the plant can run at QR2, see, right, QR2, you have to draw lines and count the durations. It is very difficult, right. But when you have the flow duration curve, if you select any flow as the rated flow, you know how much is the percentage time of the year that you can run at that flow, right, you can calculate. But if you select a very low flow like 0.5, you can see 0.5 or even less, say 0.4, then almost throughout the year you can run the plant on full load, but your plant will be very small, right, plant will be very small. And if you select say 1 cubic meters per second, right, 1 cubic meters per second, you can run about say 18% of the time full load, and balance 82% of the time of the year your plant will be running at a lower load than the rated flow, right. That means, you have spent money and have a higher capacity, but you can use only for 18% of the time the full capacity, right. And if you put what say 2 cubic meters per second as your rated flow, I will put these numbers here, I do not know whether I can draw here. There was a draw command earlier in versions, does not matter. Okay. So, you can see if I select 2 cubic meters per second, my plant capacity will be very high, right, because P is equal to Q rho G H, rated capacity will be much higher, right. But you can run only approximately 8% of the year, each site is 4%, 4, 8, 12, 16, 20. So, about almost about 7% or 8% only you can run on full load. Your plant is big, but the number of days you can run on full load is 8% of 365, right, that is less than about a month. All the rest of 11 months you will be running on lower capacities, right. And therefore, the decision on the selection of the flow duration curve will depend upon how much is the tariff you are getting. If you are getting a very high tariff, you can even go for 2 cubic meters per second and have a very big plant, right, but it can run only a few days, maybe 20-30 days on full load, but you can afford to have higher capacity, spend for a larger plant, because your tariff is high, you can still afford to do it. But if your tariff is very bad, very poor tariff you are getting, then in that case you can't do that kind of work, then you will have to go for a lower flow duration curve, rated flow, lower rated flow. So, that your plant is now having lower capacity, plant cost will be lower, because you can't afford to have extra capacity, tariff is poor. Therefore, depending upon tariff you will select the plant. Or on the other hand, I can say another way of deciding this is to select maybe 3 or so number of the rated flows and theoretically design 3 plants and estimate their project costs and then do a financial analysis and see which capacity brings the or which flow the rated flow corresponding to rated flow will bring the highest return on investment. If you go by IRR, which will bring the highest IRR, and then accordingly decide the flow duration curves location where you should have the rated flow, right. So, I will go back to again our PowerPoint presentation. Here you can see. So, in the flow duration curve, right. So, whether to go for Q1, Q2 or Q3 as the rated flow will depend upon how good your tariff is or how your project costs are. If your project costs are low, because labor is cheap, equipment you got cheap, and also the construction material costs were cheap. If your project costs low also, then you can justify a higher flow rate, rated flow rate, because your then return on investment is the deciding criteria. Whether the plant corresponding to Q1, right, will bring the, I think hope you are familiar with the terms like return on investment or internal rate of return. These are financial terms. IRR 1, this is IRR 2, internal rate of return. Q3, IRR 3. So, which is the better one? Which is bringing the higher financial returns? Then select that one as the rated flow. Sorry, right. So, that is the criteria on deciding the rated flow of a small hydropower plant, right. So, in Sri Lankan tariff, projects in this range are justifiable, maybe 15 to 20% range. It depends upon the situation the country or your state is offering, the tariffs offered by them. If the tariffs are very good, then you can go for this side, right. If the tariff is bad, lower, right. So, the ideally the rated flow should be decided by financial consideration, which project brings the higher return on investment, right, which project brings the higher return on investment. So, in Sri Lankan condition, we know it is somewhere here because of the tariff paid in Sri Lanka, but I can't recommend that for you, right. So, you must find out from the flow duration curve what should be the one that is applicable for you depending upon the return on investment after doing a cash flow analysis, right, after doing a cash flow analysis, which a financial expert can do, again accountant can do, right. Right. The selection of QR at lower exceedance will result in a power plant with lower plant factor. For example, in the above example, if QR equals 1 cubic meters per second corresponding to an exceedance of 12%, plant will operate only 12% of the time during the year at rated capacity. During the balance 88% of the time, plant will operate below the rated capacity. Therefore, the selection of QR will depend on economic considerations such as tariff, cost of plant construction, etc. If the tariff is high, even a lower plant factor will be economically viable, right, economically viable. So, you can go for a higher rated flow. Now, we know the rated flow rate, therefore, we can calculate rated plant capacity, right, and we have here I have used a term called net head, H net, because there are losses in the penstock, right. So, we introduce a term called gross head, right, minus losses, head losses, and then calculate net head, right. Therefore, net head is equal to gross head minus head loss. Head loss we will keep generally about to 5% of the available head, right. We will keep it less than 5% of the available head in our penstock design, right. Penstock will be designed, its diameter will be decided, and so that head loss will be not more than 5% of the available head, right, available head, right. So, gross head is the one that you can decide from the physical surveying or by looking at the contour lines. Theoretically, looking at the 1 to 50,000 maps contour lines, you can say upper contour line weir at the weir location contour height is 800 meters, at the powerhouse the contour height is 700 meters. Therefore, the gross head is 100 meters, gross head is 100 meters, from which you have to deduct the head losses to get the net head. So, this will be then your rated plant capacity, right. So, you can call your project 5 megawatt, 3 megawatt or 1 megawatt after this calculation, after deciding the rated flow, right, and deciding the head loss, so that you can get the net head, then you know exactly what is your plant capacity, right. So, once you, there was a question some other time, how you decide the project, the turbine type for the project. We are going to address the turbine types later, but here is a answer for that question. You can see here is a turbine application chart for hydropower plants, right. You can see here the horizontal axis is flow rate Q, right, cubic meters per second. Vertical axis is net head, right. So, you can see if our project has a flow rate of, say, this is in logarithmic scale, right, 3 cubic meters per second flow QR, right, and if the head is say 100 meters, then you come to a point like this here, somewhere here, right. And now you can see what type of turbines are suitable for your location, because this chart shows if you are here what type of turbines could be applicable. You can see now this location is lucky, red line is, red cage is Pelton turbines, right, and yellow cage is Francis turbines. You can go for either Pelton turbines or even Francis turbines, or even a Turgo turbine is possible. You are very close to the boundary, right, even a Turgo is okay, but you can't go for cross flow, right. You can't go for Kaplan, right, you can't go for Kaplan. So, this is a turbines application chart, right, typical turbine application chart. This is designed by doing various experiment by turbine manufacturers, like the specific speed of the turbine and other data they look at, and then they prepare the tables like this, right, and then this can be used by engineers for turbine type selection, right, turbine type selection. So, when we discuss about the turbine types in a separate discussion, we will go into more details. Here is the typical water cycle that we talked about earlier, right. So, what happens when the rain falls into your catchment area, some will be evaporated, some will be transpirated, and wind will blow break this whatever the clouds into some other regions, and some will be taken into subsurface transfers, etc. Only a small amount will come to your river, right. That is what the hydrologist studied with his expert knowledge. Here is a more details about what happens when the rain falls on catchment area, right. And now, right, now you can see now hydrologist has given us data and we have determined this flow duration curve, etc., etc., right, etc., etc. Now, all these are estimations, right, all these data sets were estimations, right. Now, hydrologists also use 30-year data backward, and therefore, he predicted what can be expected, but in spite of that there can be very dry years, there can be very wet years. He has given the average expectation, right, average expectation. So, he can't guarantee every year you can get those flows, right, but now No, anyway there are uncertainties in this. He says 75% probable data set, right. Therefore, now once you have decided gone up to this thing, it is good to measure the water flow rate in your river now, and to have at least a few months, so at least 1 year's actual measurements to confirm whether the whatever the hydrologist has given now in agreement with the actual measurements, right, in agreement with the actual measurements. So, for that we will construct a measuring weir, right, measuring weir across the river, right, or else we can use an approximate method. Now, suppose you visit the site one day, right. So, you can you know that you can ask from the villager there how much is the flow rate today. He might say today is lower because it was dry these days, etc. And then you can measure it that day by approximate method. So, you can get the cross section of the river, right, by a stick you can measure at equal distance, and then using trapezoidal law etc. You can for each trapezoid you can calculate the area, right, and then get the entire cross section, right, entire cross sectional area you can measure with an approximate method by dividing into trapezoid or rectangles or whatever, depending upon the shape of the river bottom. You can get a villager to get all these measurements and approximately get the cross sectional area of a place, right. Then you can measure the surface speed, surface water speed. You can put a float, something to float, and measure the time taken to go a certain distance, right. But you can measure only the surface speed, you can't measure the speed will not be uniform, right. Average speed you can't measure, you can measure the surface speed by using a floating object. Take your watch and watch time 1 minute, what is the distance it has gone, and then you know the surface speed. Once you know the surface speed, you can use this approximate formula, average speed to be a constant time surface speed. This constant is about 0.6 for rocky beds. If the bed is rocky, rocks are there, then it is about surface speed multiplied by 0.6 will be the average water speed. If it is a smooth surface, it is about 0.85 times the surface speed. These are by experiments, right. Hydrologists have done experiments and they have come up with these numbers. So, where you measure this water speed, right, water speed, surface speed, multiply by one of these numbers depending upon the nature of the bottom of your river, calculate average speed, V average. Now, you have calculated the area, total area of the cross section of that location, and V into A will be your Q on that day, Q on that day, that the day you visited the place. And now, you refer that to your hydrologist data set, and you know the date, right, and you have measured this and see whether it will not be exactly matching, whether it is in the range. If the hydrologist has said it will be 1.8, and if you get, even if you get 3.2, okay, you are in the same range, but if you get 13.2, then there is something wrong, right. They must be tallying in the range, right. Therefore, if you get this, there is something wrong, right. So, if it is 3.2, maybe in this may be a rainy day, rainy year, you might get a higher one, but they are in the same range. So, you can be sure, you have some confidence that the hydrologist values are in agreement with the actual data, right. And also for the flow measurement, there are other methods like velocity head rods. There is a rod like with the cross section like this, we call it a velocity head rod. So, we keep it against the water flow, and then height will increase by hitting. When it hit here, water height will be a little high because of the speed, surface speed, and you measure that, and this head has been tested for this height against the surface speed in labs. So, if your height is h1, you can calculate what is the surface speed using this chart, right. the velocity head rod has been calibrated, and this chart, this graph has been produced. Right, with that you can, this is another method of getting the surface speed rather than using the float method, right. So, this is, so using this also you can get the height. So, you can correct it. So, the depending upon the previous equation, we can calculate the average speed using 0.6 or 0.85 depending upon the wet condition, once you get the surface speed. So, this is surface speed. And now you are now, so the day you visited, now you took a measurement and you are happy, now they are in agreement, but this is not good enough, right. This is not good enough. Therefore, we will go for a continuous measurement, right. We will go for a continuous measurement. For that, we will construct a permanent, maybe a weir, measuring weir, right, measuring weir across the, maybe a place where the river is not very wide. We will select a place and construct either a rectangular, this is a rectangular weir, right. This is a V notch, what you call V type shaped weir. So, the water will flow across it, right, and the water height you can measure. You can have some markings here and water height can be marked. Here also you can mark here. Somebody can go there and every day take the measurement. This is marked here, what is the water height, right. And then using this formula, you can calculate the flow rate for that day, right. It depends upon the parameters of the V rectangular notch, or if it is a V notch, you can use this formula, right, and calculate that day's flow rate. So, you ask some village boy every day to take a measurement, and call you and tell, maybe once a week he will give you last 7 days, he will tell only the height. Once you know the height, you can do your calculation and find out what is the flow rate, right. So, that will make your the estimation will be checked further. What the hydrologist gave as the flow data, we will have a second check, because we are spending lot of money for the project, and if the flow data somehow is wrong, then our entire expectation of energy generation will be affected. Therefore, it is always better to double check, right. So, in the both projects we did in Sri Lanka under my this thing, we constructed this kind of measuring weirs. So, this is in the one of the 2.5 megawatt project. Before doing the project, we had about 1 month 1 year's flow data, 1 year's flow data. Therefore, we were assured that the data set given by the hydrologist is dependable. And for the other project also, it was a little narrow, it's a wide, narrow bit, this is a narrow place, we could easily do it, but the other one was a bit wide. So, we had to do a bit of a construction. We used the natural features of the river also, right, and selected on a rocky place and constructed this rectangular weir, and we also got about 1 year's data before we actually invested in the project, and we could confirm hydrologist calculations are correct. Okay. So, I have published a book based on my experience called The Development of Small Hydropower Plants, Practical Information, and this is available in Sri Lanka, and so, but I just put it here, right, for your information. Okay, we will stop there for the current discussion. Thank you. We will take a small break and then start, maybe 10-minute break, and we will start. This I will keep, or you want to take it first, speak. Okay. So, we will go along with the discussion on the design of penstock pipes for small hydropower projects, which is an important component in the design of a small hydropower schemes. So, the main task of the penstock is the intake water under pressure, to take water under pressure to the turbine. When penstocks are selected for small hydropower projects, following matters are considered: the diameter of the pipe and the pressure the pipe has to bear, the method of jointing, the length and the weight of the pipe pieces so that they can be handled at site, the maintenance requirements and the expected life, nature of the terrain where the penstock is erected, how quality of water, climatic conditions, quality of soil etc. are affect the pipe. So, these considerations must be made so that we do not have to that we make a wrong decision and be having a problem while the plant is in operation, because the penstock has to operate, as I said earlier, to 30-40 years, right. So, you can't replace it in between, which is very expensive, right. Therefore, we have to consider all these things in taking a decision. So, when designing a penstock, two parameters need to be determined: diameter of the pipes. Diameter of the penstock pipe should be determined to keep the head loss in the pipe to acceptable limits. So, we earlier said the plant should be designed to have a net head of at least 95% of the gross head, that is to keep the head losses limited to a maximum of 5%. Then we need to determine wall thickness of the pipe, because the wall thickness is required to bear the pressure. So, the pressure for the penstock will be highest at the entry to the powerhouse, because then you have the full head operating, and at the forebay tank pressure will be minimum. Therefore, your penstock need to have higher thicknesses at the bottom parts of the penstock, right, bottom parts of the penstock. In the diagram you can see in one of our projects how the penstock was under construction. So, you can see each piece you can't handle two heavy pieces. So, we limited each piece weight to about 2.5 tons maximum, so that the people can handle them with manual means, because you have to align them perfectly before welding, right. You have to align them perfectly before welding, right. And also you can see this these pipes we bought from a company in Indonesia, right. They are spirally welded pipes. You can see here in the factory they are spirally welded, right, spirally welded and X-ray tested. The welding has to be tested using X-rays, so that there are no weak points or air pockets in the welding, because these are to undergo heavy pressure. If you have bad welding, then they might on the way result in leaks, water leaks later on, right. So, a pipe with smaller diameter will be cheap, but the head loss will be high, right. Smaller diameter means more restrictions for the water flow, therefore, more head loss, right, will be high, and due to the high water speeds the pipe will subjected to high surge pressures when valves are closed, right. The head loss due to water flow in the pipe has two components, right, frictional component and turbulence component. Head loss due to turbulences and head loss due to friction. Friction comes from the surface, right. Turbulences come from the various other equipment we install in the pipes, maybe a valve, right. Valve, due to presence of the valve, water flow will not be laminar, smooth, right, it will be disturbed, some turbulences will be increased, right. So, head loss due to friction and head loss due to turbulences. So, head loss due to friction can be calculated using this formula. This is from hydraulic engineering, right, 6.3 into length into NV. N is the friction coefficient of the surface, V is the water speed, mean water speed, and D is the diameter of the pipe. Capital D is the diameter of the pipe, right. So, this will be the frictional head loss, right, frictional head loss or head loss due to friction. And this friction coefficient for different materials are in this table PVC 0.009, because in very pico hydro projects sometimes very small, maybe 5 kilowatt, sometimes PVC pipes are used as penstocks. You may have seen, I have seen some pipe, some plants, very small plants, they use specially manufactured PVC pipes for penstocks. Steel 0.012, galvanized steel has a higher, because galvanizing will increase the surface friction, surface roughness, right. Galvanized steel, concrete 0.12, right. Sometimes for a very small projects, heads, projects with very small heads, maybe large large water volumes, but pressure is low because of the low head. You can use concrete pipes, right, instead of a steel pipe. So, you can calculate frictional head loss using this, right. Turbulence head loss we have to calculate separately, right. So, the head loss due to turbulences can be calculated as k v squared divided by 2 g, where k is the you can see the loss coefficient, that is that different components will offer different turbulences. So, valves will have a different loss coefficient, bends will cause different turbulences, constrictions, when you change the pipe diameter from one to other, right, that will load D1 to D2, that is a constriction, will offer certain turbulences. And then when the water enters at the forebay tank, right, how it enters, whether it is a smooth connection or whether it is a rough connection, will cause certain turbulences, right. So, we will look at how to calculate each of them, right. Head loss due to valves, right, depending upon the type of valve, turbulences will be introduced. For spherical valves, I am sure you have seen spherical valves in your home sometimes, they do not have any turbulence, it is very smooth flow, right. But gate valves will have some turbulences will be generated. So, the coefficient they have found by experiment is 0.1, butterfly valves 0.3, right, more turbulences because of the presence of the turning parts there, right, butterfly arrangement, right. So, we can see in our project what will be the turbulences offered by our valves, for example, main inlet valve or whatever it in the penstock, connected to the penstock, right. Then penstock due to the turbulences due to bends, when a bend is there, right, can see some turbulences can occur, right, because the water comes and change the direction, right, and also this is a welded place, right, there are many welding joints here, right. So, there can be turbulences. So, it will depend upon diameter of the pipe and also radius of the bend, right. Radius of the bend, right. So, with the ratio R and D 1, 2, 3, 4, this ratio, and for different angles, bend angles, right, different coefficient will come. So, we can from this kind of a table you can get the number for your project. So, you will have number of bends in your penstock. Penstock will not be straight, depending upon the land profile, it will have both horizontal as well as vertical bends, right. You can't route it straight line, there will be many difficulties in taking it in a straight line, right. So, depending upon the land profile you will have, I will show you some photos later on, right. You can, depending upon your shape of the bend, at each bend you can calculate what is the offered loss coefficient. then reduction of the diameter if any place, if you have changed the diameter of the pipes, then accordingly you can, depending upon the two diameters, right. So, you can calculate what is the offered turbulences coefficient for the loss coefficient for the creation of due to the turbulences. Then at the entry of the water at the forebay tank. So, if you have your pipe like this, 1 very high coefficient, right. If it is flat, 0.8, if it is a rectangular like this, 0.5. If you can make it smooth, it should be smooth like this, then it is 0.2. Right. So, it is important how water enters your penstock, right, how your water enters the penstock. Otherwise, turbulences will occur, right. Turbulences are energy losses, energy losses. So, then you can calculate your total loss coefficient, right, and multiply by average water speed squared divided by 2g. That will be the total head loss due to turbulences, right, total head loss due to turbulence. Now, you calculate the total head loss, right. So, total head loss is Hf plus Ht. We will try to keep it maximum to 5%, but better to keep it in the range of 2 to 3%, let us say 3% of the head, of the gross head. If the gross head is 100 meters, make it maximum of 3 meters, right, maximum of 3 meters. So, accordingly decide D, right. So, your previous formula, they contain the term D, right. All these calculations will depend upon the D, right. So, your all these Ht and Hf terms will have the term D, right. Even here can see the term D is here, right, but they are in non-linear forms. So, you will have to put some typical values and select the one which is fulfilling this criteria, which will fulfill this criteria. So, it is not a linear equation to solve, to the d to the power different terms. So, you can select from, there are standard diameter, you can't select diameter of 31.1 centimeter. This is not produced by manufacturer. So, you are go to manufacturer's site or a standard and look at what are the standard diameters and select the nearest one for you and see whether it fulfills this requirement now, and accordingly select a suitable, because when you come to actual designs, this linearity is not there. So, you will have to do some experimentation and trial and errors and then select a suitable diameter, right, suitable diameter. Then how to decide the thickness of the pipe walls, right. So, the thickness of the pipe walls depend upon the pipe material, what type of steel you are using, what type of other material, diameter of the pipes and the operating pressure on the pipe, right. Because the diameter of the pipe is causing that you can't handle pipes. If it is the diameter is large and the thickness is small, then what will happen? The shape will change, right, when you handle pipes. So, you have to worry about that, right. So, the operating pressure caused by both the static pressure and the dynamic pressure or the surge pressure, right. So, the operating pressure is equal to static pressure is the H rho g, H is the height, water height, right. The pipe is subject to if the penstock is like this, depending upon the location, it is connected to the forebay tank, water level is here. From here, how much is the head for this location? So, this at this location static pressure will be H rho g, right, and then the dynamic pressure is different, surge pressure, and the pipe is subjected to both, right, static pressure. So, when the pipe plant is shut down and all the valves are closed and so on, only the static pressure will act. But once the pipe plant is in operation and when you open and close valves, right, then dynamic pressures will apply. We have to look at what is the possible maximum dynamic pressure, right, maximum dynamic pressure. We should design for that maximum dynamic pressure. So, in this deciding the surge pressure, we have to calculate what is called this wave velocity of the surge, right, and the critical time, right. The critical time is given by the length 2 into length divided by the wave velocity, right. The critical time is the one important one. You must avoid closing your valves, right. If you do it shorter than the critical time, you will have more surges, surge pressure. I am sure you have some experiences like this at your home. In the olden days, we had in the home water system valves where you have to rotate many times, maybe 10 times to close, 10 times to open. But the modern valves are not like that, just 90 degrees turn, right. Now, your closing time is much shorter, right. So, when you close and open these home valves, new valves, you will see the flexible cables in your bathroom will jump, right. That is because of the surge pressure created by quickly closing the valves, right, quickly closing the valve. This was not with the olden valves where you had to rotate many times. So, you do it take much more time than the critical time, right. So, no issue, but with the modern valves it is not like that. You close in maybe 10 seconds. So, that surges are generated and which will go and you can see it in the flexibles connecting your various wash basin supply to the main system. They are flexible wires at the corner. It will move because of your quickly closing of the valves. That is the surge pressure, right. To calculate that time, you can use this formula. This again from hydraulic books, right. Various terms are there. I have given this bulk modulus of water. Do not worry about these things. You can get these things from handbooks, right, handbooks, and then you have to only worry about the units. You have to put the correct units, compatible units, right, otherwise they will not match. So, the magnitude of the surge pressure that occur in the pipe when the plant is in operation depend on the rate of change of water flow due to operation of the valves or gates. If this change in water speed happens in a shorter time than the critical time, maximum surge pressure takes place. If the valve is closed instantaneously, the entire length of the penstock will undergo this peak pressure. When the time taken for closing the valve increases, a proportionate length of the penstock will undergo the peak pressure. If the valve closed in the critical time, only the valve will undergo the peak pressure, and so on. There are many parameters, but we do not have to worry about that. We calculate the peak pressure and design to that peak pressure. That is the possibility, because you know that what happens is, if you have this final water jet, right, your needle valve will be like this. From here you will have a needle moving up and down. So, this will be moving up and down to close and open the final jet, water jet hitting the turbine, right. So, this will go up and down depending upon your signals coming from the control system, hydraulics, and it will be operated by the hydraulic system. So, this water jet will go and hit the turbine blades, right. And so, the amount of water going will be dependent upon this movement of the needle valve, right. But you can see, due to some reason, needle valve can go and quickly instantaneously close the valve, creating a surge, right, due to some malfunctioning of the hydraulic system or due to some wrong signal, it can go and close instantaneously. Therefore, we must design for the peak pressure, peak surge pressure, right. So, the peak surge pressure is given by this velocity, average wave velocity, into change of speed. We can take as flow rate, water speed here, right, water speed here, because instantaneously it can change to 0, if the valve closes instantaneously. So, we will take it as the maximum possible, right, and divided by G, and we assume this pressure is subjected to the penstock is subjected to this pressure plus the static pressure, right, plus the static pressure, and accordingly design the thickness, right, accordingly design the thickness, right. So, it will not be uniform throughout the penstock for the entire penstock. Therefore, we can't have continuously change in thicknesses. So, we will have some section to have say 8 millimeter thickness, in the next another section to have say 15 millimeter thickness, in the bottom part of the penstock to have maybe 20 millimeter thickness depending upon. So, we will conveniently select what is available in the manufacturer's facilities standard thicknesses and the diameters. We will select some optimally, because you can't buy pipes with continuously changing thicknesses, that is not practical. So, we will have to select some depending upon the length of the penstock suitable thicknesses, so that your cost also goes down and also your practical limitations are also there. And there are many practical issues in that when you are buying okay, we will look at first the the total this I have already given, right. So, you can get the total static pressure plus the surge pressure, and the wall thickness you can calculate from P d divided by S. S is a safety factor, right. Maybe you can use 3 or something like that safety factor for, because we do not produce in the designs, we do not use the limited value, the final limited value for practical operations. And also thicknesses we will add some about 2 millimeters for corrosion allowance, right. We will, after calculating the thickness, we will allow about 2 millimeters extra for the future corrosion possibilities, because the pipes will corrode over the years. Therefore, to keep about 2 millimeters corrosion allowance is also practical, right. So, we can calculate the thickness using this method. You know that when designing the diameter, sometimes we calculate one diameter, right. Sometimes we will go for slightly different diameters for the transportation requirement, because suppose your diameter is 1.5 meter, right. Normally, we transport these things in containers, right. So, if you put them in a container, maybe you can put 3 of them, only 3 pipe pieces, right. So, it is a waste. So, your shipping cost will be much higher if it is getting from some outside the country. Therefore, what we do is we have some section with a slightly smaller diameter, so that you can insert them inside the larger type, maybe about 2-3 centimeters smaller diameter, and then you have a small reduction and another diameter for some section, for the practical reasons like this, right. So, you have to worry, otherwise your shipping cost will be much higher, penstock will be, total cost will be much higher. So, normally we do this kind of arrangements to economize the shipping, right, shipping and transport, even ground transportation. Otherwise, you can put only 3 pieces in one lorry, right. Now, you can put 6 pieces and so on, right. Okay. Next one is we have to consider, when you are really installing these pipes, right, in the ground, what are the other supports that we have to give, right. So, on the first place, there should be supports, right, supports for the penstock, and also anchors for the penstock, as we are going to see, right, later on. When you have a bend, when the forces change, there are dynamic forces and static forces, we will see them later. So, they will have an upward resultant at every bend. What will be the result? Under operation, the forces will try to take it up. Therefore, you must anchor it with concrete block, right, and the weight of the concrete block will depend upon the forces that are developed at bends. Right. So, other than the anchors, on regular intervals you must have supports, right, carry the weight of the pipe and water. Right. So, you can see the if the pipe weight is Wp per kilogram per meter, Ww for the water per kilogram per meter. So, they will have, you can see, total weight will have a component perpendicular to the pipe F1 and a component parallel to the pipe, right, between each support. So, this will have a component parallel to the pipe and perpendicular to pipe, right. So, these they have to be handled, they are significant numbers, because the weight of the pipe is about 2.5 tons and water will be having a substantial weight. So, all have to be borne by the supports, otherwise the pipe will deflect, right. So, you can calculate this F1 and F2, WPW, this the angle is theta, cos theta and sin theta, right, two component, right, cos alpha, alpha, cos alpha and sin alpha, right, so one parallel, one perpendicular. In addition to when the pipes move due to expansion etc., a frictional force F3 will act on the pipe as well as the support, right. Now, you can see now these pipes, right, if the pipes are held at both places by anchors, right, when the temperature changes, that pipe will bend because of the expansion. This will happen especially when you empty the penstock for some repairs or anything, because when the water is there, it will be water temperature, right, maybe 25-30 degrees in our conditions, maybe even lower in some part of the country, right. But anyway, it will not change very much, even if the sunlight falls on it, the temperature will not change very much, maybe 2, 3, 5 degrees will change from the water temperature. So, the temperature range change will be insignificant. But when you empty it, empty the penstock, and when the sunlight falls on the empty metal, temperature can go up to 40-50 degrees because of the sunlight falling on empty penstock. Then if you are holding at two places, right, rigidly, pipe can warp, bend, right. Therefore, you must have a expansion joint. Expansion joints are normally kept at the just below the anchor here. Expansion joint will have a cut here, right, and a covering arrangement here with bolts and all that. Theoretically, there is a opening or gap in the pipe ends, and there is a means of leaks are prevented by seals, water seals, right, expansion joints, and thereby the pipe, when the expansion requirement occurs, pipe can expand upward, and the amount of gap will decide depending upon the expected expansion, right. So, expansion joints are there, right. So, therefore, we have to mind all these things, right, and accordingly design the penstock, right. So, then now what happens is, now what happens, now expansion occurs, right, and when expansion occurs, pipe will try to move this way, right, on the support, right, on the support pipe will slip, right. As soon as it tries to slip, a force will act on the support, frictional force, right. Therefore, your support should be able to withstand that force, otherwise support will propel or that feel it, and then it can be inclined or whatever, right. Yeah, you have to calculate the frictional force that is possible on the support, and accordingly support should be. So, the supports will have these forces on one hand, these two forces will be acting on them, one is perpendicular, one is parallel, right, and then frictional force depending upon the perpendicular component into the friction coefficient, right, into the friction coefficient will act upon the support. So, we have to tell the civil engineer, in your design of your support you should take all these things into consideration, because he might not be aware of this penstock movements and everything, expansion and everything, he may or he may not, but we have to tell him these are the forces that will come, right, accordingly design the support. So, so the support will have a good base, right, good base and sufficient reinforcement, right, to bear all these forces. Right. So, the friction, there are different friction coefficient, right. If the penstock is kept on a steel sheet, if you can put a steel sheet here, friction will be different. If you can put some grease also on the steel, it can be different, or you can put a nitrile rubber or something, then it will be different, and so on. Friction coefficient will be different, right. So, I have given some typical values here. Here in one of our projects we put nitrile rubber here, right, nitrile rubber, because otherwise what will happen, all the paint will be over the years will be damaged by the movement, right, and corrosion will happen there and the pipe will get damaged, right. So, some people put steel plate and grease here. In here we decided to put a nitrile piece here, nitrile rubber piece, which is very strong. So, which will not damage prevent any damages to the paint, right. And here you can see supports coming up. Here this has a big base, you can see, which will going substantially into the earth as well, right, because otherwise they will be moving when the penstock moves due to friction and other things, right. They should be able to bear the static weight, dynamic forces, as well as allow the movement, right, allow the movement. Typical values for these supports, right, some PVC pipes and for steel pipes, depending upon the diameter, these are some typical distances we keep between supports, 8 meter, 5 meter and so on. Due to practical consideration, we have them because to avoid any problems with the supports later on between damage, but these can be further optimized. Here is an anchor, right. Anchors are required, we will look at the forces later on. Anchors are required to hold the bends, pin the bends down to the earth, so that unnecessary forces cannot move the penstock, right. That in a anchor you do not need much strength, you do not need lot of reinforcement. What is needed is the weight, right, what is needed is a weight. So, we just put a few little reinforcement just to keep the concrete together and then put the concrete inside, and sometimes we put what you call a plumb concrete to economize. Plumb concrete is you put some concrete and put some rubble pieces, this rock pieces into it, because it is the weight is the matter, not taking much any other forces, that it should be weight should be enough to hold it down, penstock down. So, we call it a plumb concrete, like plums in a bun, we put rock pieces to economize, right, economize. But that practically when you are doing this, what happens is you ask the contractor to put concrete, rocks, some of them that to economize they take wooden pieces from outside and put them also there, right. So, they do not understand the principle, wooden pieces they do not have the weight, right, but they economize by putting these things, because they do not have to spend on rocks. These things are done in the jungle, right. So, unless your quality supervisor is not there, these contractors will play all these things. So, you have to watch. So, quality inspection is also a must therefore in constructing these things in remote areas, right. So, the forces acting on the pipes, right. So, there will be the perpendicular component of the weight of the pipe and the water that will come into the into the anchor as well, just like onto the support. When the pipe moves due to expansion, the frictional force, right, that will also come on the penstock. The parallel component, the weight of the pipe from the anchor up to the expansion joint. You can see. Here. So you can see now this anchor will have to bear, all the weight of this. Suppose the expansion joint is somewhere here, where the pipe is discontinuous and the upper anchor is here, right. So, from this point, from the expansion joint opening point down, right, all the weight of the water and its parallel component will come on the anchor, right, and the frictional forces, when the friction is acting on the support, opposite friction will be on the pipe. So, that will also be coming onto the anchor, and the weight of the water will be coming onto the anchor, right. So, all these things have to be considered. The perpendicular component of the weight of the pipe and the water between the two supports nearest to it, right, and when the pipe moves due to expansion, the frictional force. The parallel component of the weight of the pipe from the anchor up to the expansion joint above it. So, all these things you can easily understand, right. Then the forces due to static pressure. Now, you look at this piece of the bend, this piece from this straight part to the this straight part and the bend part. So, if you look at this bend part, right. So, this pressure, static pressure here will be acting on it, on this direction, and on the other hand from this side it will be acting on this, right. So, this part will have a net force in this direction, this static pressure will have a net force in this direction, which will have a resultant in this upward direction, right, which will try to take the bend up due to static pressure. So, this formula can calculate it depending upon various angles, right, and that is due to static pressure, right. And then water flow, due to water flow, right. So, can see the water flow will have a dynamic pressure, right. So, again in the same direction, right, Q rho V, right, with these angles, right. So, they will have a dynamic pressure in these directions and finally an upward thrust, right. Again you can calculate using this formula, right, and so this will happen only when the plant is in operation, when the water is flowing, right, when the water is flowing, right. So, because of the change of the direction, water goes and hit this surface, right, and due to that a force upward is created, but you can calculate it using the change of this momentum, change of the direction of the moment of water, right. I will not go into showing this calculation, how to derive the formula etc., which you can do it if you want by referring to a textbook, but you can use it, right. And here are some, so after taking into account all these forces and the properties of the soil, right, at the proposed location of the anchor, a suitable anchor should be designed and constructed. As name suggests, the anchor holds the pipe securely to the ground by its sheer weight. More than its strength, its weight is more important. Therefore, when building anchors, an effort is made to reduce the amount of steel reinforcement and increase the weight. A popular method of doing is to use a plumb concrete. Another problem the civil engineers face when designing anchors is when the bearing capacity of soil at the location is very poor. In that case, naturally the base of the anchor need to have a larger cross sectional but the available space as well as the increased cost become major concern. So, you have to optimally design it by taking into all these factors into account. Here is a large, can see anchor, because this place the soil was very bad. So, we had to design a large anchor to increase the cross sectional area of the bottom, so that the earth can bear it, otherwise it will go down, right. And also the bend was big, and you can see here the expansion joint here. This is the expansion joint. Always expansion joint is below an anchor, right, not on the upper side, then otherwise it will come clip down. Always at the upper end of the penstock between two anchors. Here is a bifurcation. Now, we wanted to put two machines here, two turbines here. Therefore, one penstock comes up to here and then it divides into two pipes. But then lot of forces will be developed because of the change of directions. Therefore, you fabricate the bifurcation metal pipe division and then embed it in a big anchor, that big anchor, and you can still see here the expansion joints, that in both cases. This is near the powerhouse where the pipes is to enter the powerhouse, right, to the two turbines. Okay. So, we have come to the end of the discussion on the penstock design. So, we have determined to determine the thickness and the diameter of the pipes on one hand. On the other hand, design the supports and anchors required for the installation of the pipeline. So, if we do not do it, I have seen some power plants where the penstock has been completely destroyed by the forces, and they have abandoned the power plant because they were beyond repair, right. So, therefore, penstock design and their construction, installation all should be done in accordance with the applicable meeting the applicable standards and quality requirement after doing all the calculations. Okay, we stop there for the discussion, and if there are any questions, I can take a couple of them now. Yes, can you give the mic for here?
Hello. Sir, can a single 4-bay tank can handle multiple penstocks?
Yes. Yes.
Or we can build different 4-bay tank for that?
Yeah, normally we will if you have say 3 turbines, and if the 4-bay tank, if it is a low head project, then you can start, rather than having a bifurcation, that is bringing one pipe and dividing into 3 later, you can bring all 3 pipes on the one 4-bay tank, that is economical, right. But if it is a long penstock, it is more economical to build one penstock and then divide it near the powerhouse, it will be more economical. It depends upon the head of the project and the length of the penstock, etc. So, I have seen very long penstocks and then they divide into 3 or 4, but short penstocks, then you can, if you have multiple machines, then better to have straight away from the same 4-bay tank pipes, more economical.
Thank you, sir.
Excuse me, sir.
sir.
Hello, sir.
Yes, I
Hello,
can hear,
sir.
yeah, I can hear you.
Yes, sir. This is Manbir from Punjab. Sir, I just want to know the what type of the data we need to design the dimensions of the penstock beforehand. Who is providing the layout for the penstock?
Yeah,
Civil engineer or hydropower engineer is to decide.
Yeah, that's a good question. The question is, if you who will decide the number of bends and the profile, etc. That will be done by a detailed survey of the profile. So, they will do the surveyor will give you the various surveyor will give you from the 4-bay tank, right, down to the powerhouse, what is the earth profile,
Is right.
like that, right. So, accordingly you will have bends.
Right.
So, it is the survey team will give you this profile, but of course, sometimes there may be a big rock here which you can't take, then you might have a horizontal bend also, going around it, or you may avoid it. So, you have to look at all these ground features and decide the final route of the penstock, right, final route of the penstock.
Right. So survey engineer is basically providing the profile of the penstock, and then hydropower engineer is deciding the dimensions of the
that's right,
penstock.
that's right. Yeah. In reality,
And
the hydropower engineer will
yeah.
employ a surveyor to
Right.
first get this profile.
Right. Right. Thank you, sir. Thank
Okay. Okay. Any other questions? Okay, in that case we will end there. Thank you. I think he will close. Okay.
Hello, hello.
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 Good afternoon, everyone. I, Pranati Purohit, a research scholar at NIT Rourkela, welcome you back to the afternoon session of Day 2 of the GIAN course MHPDIMG 2024, conducted by the Department of Electrical Engineering, National Institute of Technology, Rourkela. The present session will be addressed by Professor Indrajit Sarkar, NIT Rourkela. I take the opportunity to introduce Professor Indrajit Sarkar to you all. Dr. Indrajit Sarkar received PhD in Electrical Engineering from IIT Bombay in 2018. He has nearly 7 years of industrial experience working in the areas of power electronic converters for renewable energy and HVDC. His areas of research interest are EV battery charging system, DC-DC converters, multi-level converters, its control and applications, modular multi-level current source converter, its control and application, induction heating, induction motor drive for high power applications. He completed his BE degree in electrical engineering and ME degree in power electronics specialization from the IIEST Shibpur. From August 2005 to June 2010, he has served as an assistant system engineer for energy and utility customers, Tata Consultancy Services Limited, Kolkata. From 2012 to 2017, he was a full-time research scholar with the Department of Electrical Engineering, IIT Bombay. From 2017 to 2019, he has served as R&D engineer in HVDC grid systems with ABB Global Industries Services Limited in India. In July 2019, he joined as an assistant professor in the Department of Electrical Engineering, MNIT Allahabad. Dr. Indrajit Sarkar joined the Department of Electrical Engineering of NIT Rourkela in March 2020, where he is currently serving as an assistant professor. I request Professor Indrajit Sarkar to address you all and deliver the presentation. Please, sir.
Hello. Thank you, Pranati. And I welcome you all to this session where I have planned to discuss the power converters that we are going to use for renewable energy extraction. And here, since this topic is on hydropower, so I will discuss, my focus will be mainly on power converters that we use for hydropower plant and some control aspect of it. Okay. So, this is the presentation outline. So, first I will give some brief about how power converters are going to help us. Actually, previously the scenario was different. Okay, maybe 30-40 years back, the aim was to generate the state of art was to generate power from coal based power plant, and then mainly coal, hydro, and then you generate that power and then you transmit that power from remote location and then use it. But current scenario is completely different, where we have distributed generation like solar, wind, this hydro, then fuel cell is coming up, also battery energy storage system. I have heard the scenario where the power utility company is not able to supply power to a particular location. They are planning to install a complete battery energy storage system to supply for that particular location. So, this kind of applications are coming up, and for those applications without power converters we cannot think of. Now, I mentioned about legacy system, this LCC thyristor converter. I will tell you what is the significance of this here, and then how to extract power, renewable energy power. We will see that it is almost similar, whether it is wind, whether it is hydro, whether it is solar. So, how to extract means what should be okay. So, what should be the how it can be extracted and looking at their characteristics. Then grid connected hydro power plant, and these are the two major and popular solution that we have for grid connected hydro power plants that we will discuss. And then how to introduce this multi-level converters for this hydro power plant. Now, first we will discuss with how this power electronics is going to help us in renewable energy integration. So, it is like let us say we get crude oil. Okay, so, crude oil, then what we do, we refine it, and then end product is like let us say diesel, petrol, kerosene that we use in our daily life. Similarly, renewable energies are available. Till now what we know, a few renewable energy sources that like solar, wind, hydro, and then fuel cell also we are treating as renewable energy. So, but it is like hydrogen is plenty of hydrogen is available, so we can treat it. So, the thing is, the sources are there, the power that they are generating, those are very crude sense. Why, what do we mean by crude sense? Because the voltage is not fixed, the current that is delivered by that source is not fixed, the type of voltage and current that is delivered by that source is not fixed. Fixed in the sense, it depends on whether it is solar, it will be different, whether it is wind, it is different, whether hydro, it is different. So, it depends on what kind of source that you have, and also it depends on various location dependent. If it is wind, it is very popular that offshore wind farms are very popular. Okay. So, that is there. Then when it is solar, then in desert it is very much popular because plenty of space is available, there you can install megawatt level solar plants. In mountain areas also we install some kind of this renewable energy sources, because the conventional grid, it is not always feasible to reach that area. So, and also these are very much dependent on weather conditions. So, the renewable energy source that we are getting, those are crude in the sense. So, therefore, to make this useful, we have to do something. So, these are the application requirements. So, these are the sources which we want to use. So, we need, so this is the application requirement, means we have to filter it out, we have to make it human usable, which is suitable for us, that power form we have to convert. So, from load point of view, if we see, so in output side what we have, we need, the initial days it was only AC, single phase or 3 phase AC. Then it is, now we are having DC microgrids and all are also coming up, also DC charging and etc. is coming up. Then the level of voltage will be different, high voltage, low voltage, those voltages will be there. High current applications are also there. There are motor drives application where you need current level higher, high current, or you need both high voltage, high current for high power application. It could be standalone or it could be grid connected as well. And then there are microgrid. So these are what we need, and here the standards are imposed, and this voltage, current and other harmonic content, everything are defined. So here which is very crude, and here which is has to be very sophisticated, or it should be very useful. It should be in such a form that it is useful to our daily life. So this is the load requirement. Now there is a huge difference between whatever application is there, or the renewable energy sources, what are the form that they are generating, and what is we are going to use. There is a gap. So how this gap can be filled? This gap can be filled by power processing unit. So it will process the power from crude sense to usable form. Okay. So here the heart of the power processing unit is power converter, that I will come up. But what are the different components that you must have in a power processing unit are? So first thing, what it could be? The first thing, what you expect? What it could be? The first thing? Power circuit will come, but power circuit is the heart of the thing. But there should be many more things which is going to support the power circuit. The first thing is you need a filter circuit, okay, if possible. So if you see any DC-DC converter, the first thing that you have is what? Before the converter, you have the filter capacitor, right? That is filter. So first thing that you need is the filter, okay. At least you filter out crude sense, in a crude way you are getting some power. So at least if possible you filter it out, okay. Same for the output side, okay. So you made something, you converted to some level, now you put some filter, you don't go further. Power converters, I remember when I was studying in my second year of BTech, one person from industry has came and explained that is still I feel that word is very much valid, that power electronics is an area using which you can do anything, whatever you want you can do, whatever voltage level, whatever current level, whatever type of voltage, whatever type of current, whatever you want to do, everything it can be done, okay. So here without this passive filter also we can do it, but we are saying we don't want to make it further complex, let it make it simpler, if possible use filters, and that filters are not active filters, these are simple passive filters, L, C, this you use or combination of this, and then you make it suitable for input side and for output side also. Then it comes to the power converter, okay. Then the power converter does that conversion it will do. So when I studied power electronics in my BTech, my professor first thing that told that power electronics is not that we are dealing with high power. Power electronics is the area where we convert this power converter, we convert type of electrical energy to another type. So it is DC is there, you are converting DC into DC, but the types are different, voltage levels could be different. So similarly it could convert DC into AC, AC into DC, AC into AC, everything is possible. So power electronics does this thing. So power converter is there. Then what is that? Power converter is the circuit, okay, power converter. So in order to make it run, what is the next thing that you need? You need a control circuit. So there must be a control. So you must have a control unit. So you have power circuit, you have control unit, and then what you have is this, okay, sensing unit. So sensing unit in the sense, this power electronic converter, in order to run it using the control unit, it should not be blind, it must be knowing what are the voltage levels, what are the current level. Similarly, so for both for the input side as well as for the output side, okay. So it must know what is coming and it must know what I am delivering. Okay, then only, so it is this control unit must be knowing, okay, this is what is I am out, my output is this, the output of the power electronic converter is this, but I am not expecting this, I have to correct it. So in order to know whether it has to correct it or not, it must sense the output. Also from the input side, input sensing unit you must have, so that it must know what is coming. Okay, you will understand when I explain this power MPPT, that time I will explain how this sensing is going to help us. Then in order to, when you, so this is fine. Okay, if you see in simulation, if you do these components, with these components, if you do simulation and your input is your output is coming fine, we are happy. Then you make an experimental circuit, you validate it, and we are happy. But this is not the case, because when you are validating something, so you must expect that it must go to a product level. Let us say you are making a converter, power converter suitable for some application. So when you simulate, then you validate, then you must think how it can go to a product level thing. If you think like that, then you must have, this is one of the most important, one is the protection. Why protection I will tell you, but let me tell you another important thing is the EMI and EMC filters, EMI and EMC, yes, EMI and EMC filters. Now why protection is important here, very much important, because when it comes to a product, protection, input output protection, okay. Why, when it comes to a product level thing, what happens, when a company is going to make a product out of it and going to launch in the market, a customer is going to buy it, and that will be based on two things. First, customer does not know how this product is going to work, he blindly will buy. Okay. Based on what? The first thing, he do not have any review from anywhere, because he is the first customer that he is going to use that product. So he do not have any review. Second thing, then what is the second thing that he is going to see? The price, right. So price, and second thing is reliability. These are the two major things that a product must have. Okay. So if you have protection unit in place, then you must improve the reliability of your product. Now next time, that if the person who is first time user, that person will use that product and he will become a reviewer. So if he is happy with that product, he will give a positive feedback, and next time another customer will come and buy that product. So in order to improve the product reliability, these protection units are needed, and in order to meet the standard, you need this filters and this EMI filters and everything. Now one of the major thing that we are missing here is, one of the major thing that we are missing here, can anybody guess? What is the major thing? Reference is there in control unit. Okay. Communication, they must communicate with each other. So everything, so you should have a communication between each and every item, right. So here, this is the complete picture. So here what we have crude renewable energy sources, and then we need that crude energy source to be in a useful form. So for that we need a power converter, but to have a power converter you need this necessary components in order to make it work. Okay, is that clear? Now today what I am going to do is, today I am going to discuss about this power converter, and for this one, for hydro power plant, I will come to that. Okay, power converter. Now what happens, depending on this application requirement, or depending upon this renewable source, and depending upon load requirement, the major component that going to change in this item list is the power converter. This is the major thing that is going to change. The type of converter, either it could be a DC-DC converter, it could be a DC-AC converter, it could be AC-AC converter. So that is why this is important. Okay. So today I am going to discuss about this, because the rest of the thing, whether it is sensing unit, protection unit, filter, passive filters and all, this is almost will remain same throughout the platforms. Now, control unit also, now we are very happy with the DSP microcontrollers implementation. So, this is also almost constant for different topologies. Okay. So, today we will discuss about power processing unit, which are mainly the power converter that we are going to discuss. Okay, this is what I already told, that choice of power converter changes with application requirement. Okay, it depends what do you want, depend on that it is going to change. So, rest of the system are going to be same, almost remain same. Now, why power converters are going to be different? What is the answer to this? Why power converters are going to be different? Why it cannot be same power converter can we use? Why it should be different? Applications are different, that is broad sense, that is correct. Different voltage level, right? Different voltage level. So, what he said is that is more prominent, because if we, let us say I am talking about let us say a very basic DC-DC converter is a buck converter, okay. But buck converters are not suitable for high power application. Buck converter 100 watt, 200 watt, 300 watt, even 300 watt is high, it's fine. But when your power level, voltage level are going up, I remember there is a very famous problem in industry, okay, I cannot tell you, but that problem you cannot solve using this buck converter, boost converter, you cannot do that. You need some other kind of converter configurations in order to address, and this is still an open problem, and researchers are working, definitely working on it. Okay. So, as you told that semiconductor technology is very much means it's growing, but thing is when let us say you thought of an idea and you thought of something, let us say I am giving you one example, vector control you heard of, right? Vector control of induction motor, that is a very famous, okay. It was invented by long back, but it was not able to, industry was not able to accept it. Why? Because that time when it was invented in 1970s or 80s, okay, by a German scientist, what happened? This DSP microcontrollers were not that much readily available in the market, or was not accepted in the power electronic circuit. So, because of that, what happened, even if that theory is in place and idea is in place, you can implement it. Since those things were not readily available, it was not accepted by industry, and it is accepted later on, and now this is the state of art of speed control of an induction motor. Okay, vector control and DTC are the two major speed control techniques that almost every industries are using because of high performance. Okay. So, here also if you go for high voltage application, the semiconductors are having limited capability, limited voltage and current capability. Now, what happens then immediately it might you might think that okay, we will connect them in series and then we can make the voltage can make it for suitable voltage level, like just like we add bricks to build a wall, right? We can do that, definitely we can do that. But the problem is when you connect anything in series, anything in parallel, what happens when you connect in series, definitely there will be a voltage mismatch between the devices. Okay. So, in that case when you want a very high reliable converter, then you must have the voltage balancing circuit in place. There are active passive voltage balancing circuits. If it is in parallel, current sharing is also a difficult task. So, those things are there. So, why can't we improve the topology and change the topology so that this voltage balancing things and series connection we can avoid, that we can come up. So, for current, so increase the current level. So, that is why, so this were the problem, okay, like high voltage, high current. Now, what happened, I can tell you this legacy system, I have the slide for legacy system. Now the thing is, thyristor is one of the very reliable and very high power electronic device, okay. Though it is not that people think about, people go with IGBT, MOSFET, high power we do not go with MOSFET, we go with IGBT. okay, IGBT, IGCT, okay, these things we go with. But previous days this thyristors were the only solution for high power applications. You heard of HVDC, right? In HVDC, I can tell you the transition because I worked in HVDC, so I can give you some glimpse of it. In HVDC, it was thyristor converters only. Okay, previously when it was started with thyristor converters. Okay, and it was installed at various places in the world. Okay, many even in India we have HVDC links way back in 1970s, 1980s. HVDC links are there. Those are completely thyristor based. That time we cannot think other than thyristors. Okay. Another advantage of thyristor is thyristors internal drop is very less, and also thyristor is not very high switching frequency device. So losses are very less. So that is why thyristors, hundreds of thyristors connected in series parallel, and somehow we are engineers, we made things working. So HVDCs are working and extremely at high reliability. The thyristor, these HVDC links are have very high reliable, means those are very reliable. Okay. But there are some issues come with it because thyristors are semi-controlled device. You cannot turn it off. For that you need high reactive power at the source and the load end in order to make thyristor commutating, means for thyristor commutation. Then what people thought, like, if we are coming up with multi-level converter, why not use multi-level converter for HVDC? Because the features of VSC, voltage source converters, are far more than current source converters like thyristor converters. Those are current source converters. Now you will see that whatever legacy system were there for HVDC thyristor based, now almost 9 out of 10 projects on HVDC are on VSC based converters. Okay. Now people have implemented, it is successfully running, okay, and it has enormous advantage, VSC converters. Okay. But since it is coming up, this VSC based converter based HVDC is coming up. So now it is the power level that they are implementing, the power level of this thyristor based converters are much more higher compared to this VSC based. Recently India has implemented one 3-terminal HVDC, those are thyristor based, maybe 5-6 years back India has implemented. It is from northeast we have huge amount of renewable energy sources, they are bringing it to Agra. Okay, the northeast Agra, this link is there, you can search over internet, you will see it. So it is through Alipurduar. So first they made one terminal at Alipurduar, from Alipurduar they made to this Agra. Why Agra? Because they are saying it is a central part of India, so it can disburse power from that place. Okay. So that is LCC based. So for high power application, LCC based converters were very much popular. So this is one of the example where synchronous motor drives were using LCC converter, load commutator converters or line commutated converters. So what happened? This is synchronous motor drives. For synchronous motor drive, what happened in older days? It was the synchronous motors were for very high power application, megawatt level drives application. Synchronous motors at high power are efficient than induction motor. That is why synchronous motor were preferred. And since it is a load commutated converter, we run it. So you can see here overexcited. So it is overexcited synchronous motor. Okay. So when you run it at leading power factor, the commutation of the thyristor becomes easier and it is feasible. That is why this was the only solution in older days for synchronous motor drive. So LCC thyristor converters were very popular and for high power application. Okay, line commutated and load commutated thyristor converters. Thyristor advantages I already told you, but it is semi-controlled device, large reactive power requirement, and since I told you it is a current source converter, so slow response is there. So this thing I already told you that synchronous motor drive leading power factor, so load commutation were feasible, and synchronous motor is efficient than induction motor at high power level. Now see the induction motor. Induction motor is such a versatile machine, it is used at each and every application, you cannot avoid it. Even it is so much popular, even it is competing with BLDC motor for electric vehicle. In electric vehicle it is competing with BLDC motor. It is 120 years back it is invented, still its competitor is very less, okay, induction motor. So now this place is taken by induction motor, the synchronous motor drives are taken by induction motor, and this induction motor drives are used by VSC converters. Okay. Now why we are switching from LCC converter to VSC based converter? So now it is DSP processors are readily available, we can control, we can implement easily, and then we have semiconductor technology like IGBT, IGCT, and control of VSC are far more superior compared to LCC. Okay. So because of these advantages, now we have completely switched from LCC based converter to completely, in the sense in some application you cannot think of other than LCC converters. So but rest of the converter we are happy with these VSC converters. Okay. Now for renewable energy sources integration, so what are the converters that we need? You need all the converters. You need DC to AC converter, you need AC to DC converter, you need DC to DC converter, you need isolated DC to DC converter. All possibilities that you need. Why you need all possibilities? So when it is solar PV, the solar energy that you are extracting and then you are giving it to grid, or you are using it for standalone application. Now output of solar is what? As a variable DC, right. So first you convert it into a DC, fixed DC, not fixed DC, because if it is a grid connected, so you need a DC to AC converter. So DC to AC converter, what you do is, first you use a DC to DC converter, where this DC-DC boost converter is one of the most preferred DC-DC converter for this solar PV application for MPPT tracking, and I prefer this converter because you have inductor at the input, you have inductor at the input. This inductor makes the current continuous in the sense, if you see buck converter, if you let us say use buck converter, the current that is going to deliver by this solar PV is discontinuous, whereas because of when you have inductor you cannot think of, generally you cannot think of discontinuous current. So you will have continuous current. Because of that, this solar, always any source, whether it is battery, whether it is solar PV panel, it always preferred that you take DC current from them. Okay, don't take high frequency AC current imposed on that. So what we have, so when it is grid connected, when the solar PV is grid connected, you need a DC-DC converter and then followed by an inverter, simple inverter that you use. When it is DC microgrid, then your converter configuration has changed. It becomes a DC-DC converter. Okay, a DC-DC converter that could have dual stage, that could have single stage, but single stage will do when it will do, let us say DC microgrid, you cannot. So if you have a, let us say a DC microgrid, okay, so this is the DC bus that is given by the DC microgrid, and here is the solar PV, then you have the converter, DC-DC converter, DC to DC converter. When this voltage is defined, so you use single converter and extract MPPT, that is you do it in current control and then you extract power and deliver to this DC bus. But when this voltage is not defined, then you need something else, then this may not be this converter may not be suitable to extract MPPT power, and also because the solar PV power varies like anything with the irradiance level, temperature level, everything. So that may not be feasible. Now this goes with solar. When you have wind energy, so grid connected, when it is grid connected, you need, when wind power extraction, what you need is AC to AC converter, because wind is going to generate 3-phase AC, and if you are connecting it to grid, you need a 3-phase output. So AC to AC converter. So in AC to AC converter, there are two possibilities. One is back to back converter, or what you use, matrix converter. Okay, so these are the two possibilities that you have for grid connected wind energy. Or if it is a a DC microgrid connected, then you need AC to DC converter. So, depending on what kind of converter, what kind of application that you have, your converter configuration is going to change. When it is hydropower, then same, you will see that for hydro and wind that almost things are similar. Okay, for hydro and wind, it is the power extraction is almost similar. So, for hydro power plant also grid connected, then you need AC to AC, and when it is microgrid connected, then you need AC to DC. So, battery energy storage just for continuity I have added. So, you need a DC-DC converter, and for fuel cell you need a DC-DC converter when it is electric vehicle application, and then for microgrid also it is DC to DC converter that you need. So, here fuel cell output is low voltage and high current. Okay. So, you see different energy storage, energy sources will have its different type of output, and you have to deal with it, and power electronic converter is the only thing that you need to deal with it. Now, you see here characteristics of these three. Okay. So, I specifically put this slide in order to let you understand that whether it is wind, whether it is hydro, whether it is PV, you will have this kind of characteristics. Okay. And depending on the weather condition, depending on your operating condition, you had to extract. If it is a layman job, a layman and an engineer difference is, engineer always, we are engineers because we always design the thing. And why we design the thing? Because we want to optimize the system operation, right. Without you put a solar panel and at your home a bulb is glowing, okay, fine, you have made it working, but when it is an engineer comes, then it should be solar PV that you install, you extract power at MPP, and then you glow that bulb. Instead of one bulb, you may glow at 2-3 bulbs. This is the difference. So, when we are engineer, we have to extract, since depending on wind speed, depending on water flow, and depending on irradiance, the MPP point are changing. So, role of power electronic will be to track power electronic converter on the source side, on the source side. The role of the power electronic converter is to extract the power at MPP, that is the sole role. So, if you have two converter, one will take care of the grid side, another will take care of the source side. The source side converter is going to deal with this MPP, whether it is solar, whether it is wind, whether it is PV, everywhere this MPP tracking will be there, and you need a converter in order to track this. Is that clear? Okay. So, need for a power converter and to control it to extract power at MPP. Okay. So, depending on characteristics, you need to implement the type of converter. Okay. Now I am coming into hydro power plant. Okay, hydro power plant. Now, what happens? The power, how the power is generated? So, you will have a turbine, water turbine, then it is coupled with a generator, right. Now, this, there is a water inlet and outlet, like steam input and steam output, this turbine and this generator. Now, depending on this water flow rate, as sir was explaining that in a river we implement several such turbine, and on the river flow rate the turbine speed will change, the turbine will rotate and power will be generated. Now, when it is river flow, then what will happen? The flow may not be constant throughout. So, this rotational speed will be variable. So, generator rotation will be variable, the output power from the generator will be variable, and how this is variable, that will depend on this, that will depend on its characteristics. Based on the water flow rate, the power delivered by the generator will be different, right. So, that is what variable speed operation is necessary. Okay. So, you have to allow variable speed operation. Constant, if you have a constant speed turbine, it will not do, because the application is variable speed and you are implementing a constant speed turbine, there is nothing out of it you are going to get. Okay. So, output power is proportional to water flow rate. So, power fluctuations will be definitely there, whatever I showed in the characteristics. So, control of power converter. So, then you role of third party. which is a power converter. So, you have source, you have turbine, and then you need a turbine generator set, then you need a third party power converter, which is going to take measures in order to get your power at smooth operation. So, two options that we have is that depends on what kind of generator that we are going to use. One is permanent magnet synchronous generator that you must have heard of. Another one is doubly fed induction generator. Okay. Doubly fed induction generator, I personally feel, is one of the best engineering marvel. Okay. In motors, that is one of the best motor that I have ever seen in my engineering career. This is one of the most versatile motor that can be controlled in a very nice sense. I will explain one part of it. I will explain. So, this doubly fed induction generator were the state of art few years back for wind power extraction. Now, this permanent magnet synchronous generator are used. Last time we were in discussion with sir. Sir was telling for wind power application, this permanent magnet synchronous generators are getting issue like this permanent magnets are getting deteriorated because of this weather condition, because wind farms are generally at offshore. Wind farms are offshore. So, harsh sea weather condition it is installed. Because of that it is this issue with the permanent magnets of the synchronous generator is coming up. So, anyhow we will explain, we are not going with the motor part, but if you have the motor, how to control that we will see. Okay. So, this is CFSM is converter fed synchronous machine. Okay. So, any motor is not generator or motor, it is machine only, it is a rotating machine only, it is you that you going to operate that machine as either as a generator or as a motor. That is why always we use this term M, that is machine, and this is doubly fed induction machine. In converter fed synchronous machine, what happens? The stator of the machine is directly connected to the grid through a transformer, or stator of the machine is connected through a power converter or frequency converter to the grid, either through a transformer or directly to the grid, depends on what kind of converter that you are going to have. And doubly fed induction machine is stator is connected to the grid, but rotor is connected through a converter, that we will see. Okay. So, what is the role of power electronics? So, role of power electronics you can see here is vast. The grid integration part is there, where you control the power flow, you can control the reactive power flow, you can control the frequency, you can control the voltage level, those synchronization thing is there, and protection is there. In machine control, what we have? In machine control we have how we are controlling the speed of the machine. Okay. Here what we have the turbine generator set, the generator speed you have to control, the speed that you can control by controlling the torque. So, how we are going to control? These are the two methods, and then the construction of the machine. Then variable speed operation, if you pump energy storage, pump storage hydroelectric plant, then what you have is you have a reservoir. Okay. So, what you do is when you need power, use that reservoir water. So, you have a tank, you have turbine generator set, so you take water from here, and then so this is water flow, so generating mode. So, using this water, potential energy is converted into electrical energy. When excess power is there in the grid and you have to maintain the grid frequency, what happens when grid power increasing, what will happen? It is not like a DC bus, it is the frequency of the grid will increase. Why? Because the synchronous generator that is running, it is getting excess power, and its speed will, rotational speed will increase, and eventually the speed of eventually the frequency will increase. In order to maintain the frequency, why not to extract some power from the grid? So, you extract power from the grid, and using this turbine, now it will work as a pump, you pump back the water to the storage. Okay. This is how it can work. Okay. So, that is why generating mode, pumping mode. Okay. And then excitation control, we will see. Acha, typical rating, mini hydro power plant if we say, then typical rating typical rating, generator rating up to, this is not a hard and fast rule there. So, typically 2 to 3 megawatt power level we can say as mini hydro power plant, but voltage level is different, up to 400 volt to 11 kV. Why for high power application we need to increase the voltage level? What is the reason? If anybody can answer. For high power level we need to increase the voltage level. What is the reason? What could be the reason? Why we increase? Loss. How will reduce the loss? So, power level increases. If we increase voltage level, then current will come down. Then the first thing apart from loss, what is the first thing that we are going to get is, in previous case, let us say we are having this much we had used, let us say when it is 400 volt, we had used this much thick conductor, because your current level is high, you have to use thick conductors. When you increase the voltage level, insulation thickness is not going to increase very proportionally. So, your conductor size reduces. So, your machine becomes compact. Low voltage, high current, machine size will increase. High voltage, low current, your machine size will reduce. You will have compact solution. Then this definitely I square R. So, I square R loss will reduce. I is reducing. I square loss R loss will reduce. So, 11 kV. If it is 11 kV, machine rating is 11 kV, or if not 11 kV, if it is a let us say 3 kV or something, it is not, 2 level converter is not sufficient to use. You have to use something else, okay, that we will see. Okay. So, this is converter phase synchronous machine, So, let us see what are the components that we have here. So, first is, this is the generator that we have, okay, and this is the stator part, outer part is stator, let us say assume the inner part is the rotor. Then since it is a synchronous machine, so what you need? You need a DC field. So, you need this one. So, you need an AC to DC converter in order to make it DC. So, DC field you need. Why you need DC field? Because it is very simple. This operation means the working principle is very simple. Stator is a distributed winding, you supply with a 3-phase balance winding, you will have a rotating magnetic field, and then you have on the rotor you have another magnet which rotates and locked with the rotating magnetic field. So, if it is a DC, it is well suited and it will lock with the rotating magnetic field and it will run. And then you have a back to back converter. Back to back converter means this is AC, this is AC. So, this is DC, intermediate DC. So, this is back to back converter, this is an inverter, this is not inverter, I should say 3-phase AC to DC, this is AC, DC to AC. So, these converters are required to control the stator frequency and also the stator voltage, that we will see. Okay. Now, in order to match with this grid voltage where it is supplying, you might need grid transformer. These transformers are the major problem nowadays. People are thinking that how to remove this transformer. That is why the concept of solid state transformer has come up. So, solid state transformer, input is AC, output is AC at different voltage level of different frequency, same frequency. Even you can have same, even if you have same or different frequency at both the sides. This is a very versatile kind of transformer with high frequency insulation, high frequency isolation. Okay, this kind of transformers are very compact in size. So, this grid transformer how to eliminate. So, one of the ways you use a converter configuration so that it can capable enough to withstand this grid voltage. Then this grid transformer, because this is required only for voltage matching. Okay. So, back to back converter, this is a frequency converter, high rotational speed with high rated power. So, when you have high rotational, so you will see that doubly fed induction machine, you have windings on the rotor. Okay. So, the rotor itself, inertia of the rotor itself is high. So, we cannot run it at very high speed, windings will come up from the slots. Okay. When it is high speed, definitely it will be a compact size. Okay. So, here since you have a back to back power converter, it is very easy to control speed from 0 to rated speed, and this is one of the very popular requirement. Rated torque from 0 speed. Rated torque from 0 speed, I can tell you what it is physically, how it can be explained. I do not know whether you have seen hoist or not. So, what is hoist? So, in industry if you go, so let us say there is a heavy component is kept here and you have to take it to that place. What they do is there are hoist throughout the, means there is a grid. So, hoist can come, lift it up and bring it to that different place, right. Now, what happens, the hoist has lifted it up, okay, lifted it up. So, in order to lift it, it has to balance the gravitational force which is pulling it. So, that means you need a torque on the hoist shaft, you need a torque, but hoist is what? It is stationary, right. That means the hoist is stationary, means it is at 0 speed, but it has to apply the torque. This is the condition, rated torque from 0 speed, that means at 0 speed you need a torque. If this is a very crucial requirement, what happens, sometime you have torque pulsation at 0 speed, what will happen, the hoist cannot hold that object, it will vibrate because there is a vibration in torque. So, it will vibrate. So, this thing you have to keep in mind, and this is nowadays this is not a very difficult task. Now, the problem with this configuration is, you can see here the converter has to cater the entire power of this machine. Okay. So, converter rating is same as that of machine. Okay. Now, you see here, since time is almost running out. So, just directly I will come, these are simple thing, grid, reactive power control and all. The main thing is this one, STATCOM. Now, what happens here, I omitted one important thing, which is capacitor. So, what happens, this capacitor and this thing, this part, as I told you, this HVDC, LCC converter, instead of LCC converter, if you use a VSC converter, it can support the grid ancillary services. So, one of them is STATCOM. So, it can act as a STATCOM and support the grid. This is one of the advantage that you are going to have with this converter configuration. Okay. So, now this control of this converter. Okay. Now, the control of this converter has two part. You can see here, one is, this is the grid side converter. Grid is there, grid side converter, and this is the machine side converter. Okay. So, machine, this is machine side converter. So, what is the philosophy? The philosophy is, from the grid you maintain this DC bus voltage, at a fixed value, okay, whatever value, that depends on what is the design thing. So, you fix the DC voltage and then you let it work at MPP. How it work at MPP? You have to control the speed of this machine at that particular speed, so that the power extraction from the machine is maximum for that particular water flow condition. Okay. So, how it can be done? So, what it does is, the speed control it is doing, speed control. So, speed control, so you will have a set speed which will come from MPP controller. Okay. So, MPP that you are going to implement, from there it will give you the how much reference speed it should be at this condition, and this converter, the role of this converter will be to attain this set speed. Okay. So, it will sense, as I was telling you, this sensing part is one of the major thing. Then you have the controller, and with this it will generate ID, IQ, whatever it is up to you, because it is convention is up to you, but it will generate the torque producing component, torque producer, whether it is ID you are taking as torque producing component or IQ. So, that torque producing component, and accordingly it will adjust the using the current controller, it will generate the reference voltage, and then it will set the converter voltage here VC, so that the current here becomes the desired current, so that the speed can be attained. This is what. So, reference speed from MPP, this reference speed you are sensing, then you will generate the reference current, from reference current you will generate the reference voltage, and accordingly the converter voltage will be adjusted for that MPP condition. Is that clear? This part is clear, otherwise I will again explain this part. Any doubt anybody is having, then I can explain once again. Okay. Now, in the grid side it is conventional thing, there is no difference, it is voltage sense, the desilting voltage control, then and then reactive power control. From here you will have ID and IQ stars, grid side current, and then you are sensing the ID IQ, and then you are converting into ABC to DQ, and then there is a current controller, you are generating the reference voltage for the voltage control of the converter. Okay. So, now it is back to back. Now, you can see here why we have back to back converter. So, one is doing the MPPT and one is taking care of the grid thing. Okay. So, this is how this is a typical control that I have presented. Now, on modification of this you can figure out what are the gaps that you are going to have with this, and then accordingly you can control. Now, this is the typical single line diagram. So, bypass means what they are saying, just quickly I will tell this. When this is synchronized, this machine is synchronized, what they are saying, they can remove it and they can bypass it, and then let it run from the grid itself, the transformer output itself. Because if converter is off, so converter losses become 0. Okay. So, possible service of the converter unit. So, that time you can do the servicing of the converter unit. Okay. STATCOM operation, I already explained this, that reactive power flow can be controlled with this desilting capacitor. Definitely size of the capacitor will be different than when you are not doing reactive power control. Okay. Now, doubly fed induction generator. In case of, so the difference here is, you can see here, the instead of DC excitation it is AC excitation, because in induction machine the rotor, the beauty of induction machine is whatever stator you are doing, the rotor will just do the mirror image of the same thing. Okay. This is the beauty of induction machine. So, that is why if stator is AC, then definitely rotor will be AC. So, what it does is it controls the rotor power, that I will show the figure, then you will understand. So, here you can see here, there since rotor power is much less, rotor power is S into PG, where PG is air gap power. So, this power is much less. So, rating of this converter is much less compared to the previous case, where rating of the converter was same as that of the machine rating. Okay. Stator is directly connected to the grid, and this is through the, okay, I have to skip this because this part. So, how this is controlled? So, how this rotor part is controlling the philosophy, I can tell you what happens. So, this power, this is the synchronous generator, this power is coming which is PG, air gap power. Okay. Now, this power is S into PG. Now, as you want to change the speed of the machine, if you control this power, that is either, so if you see here, so this is the torque speed characteristics, torque slip. Okay. So, let us say it is operating as a motor and you want to make it operating as a generator. So, if you start, so when it is operating as a motor, so the rotor power is positive because slip is positive, rotor power positive. So, rotor power is coming up. Okay. So, the power that is available on the rotor shaft is 1 minus S into PG. Okay. Now, what you do is, let us say this though this is a diode bridge rectifier, instead of diode bridge rectifier, if you have a converter like this, which is I have shown previously. So, what it is going to do is, it will feed power from this side also, it will start feeding power from this side also. So, what will happen? Your operating point will keep on shifting from here, and there will be a time it might happen the power is such that the power that you are injecting, now power is coming from both the sides. Okay. So, the machine will operate here. If you further increase power from rotor side, what will happen? It will now start going to generating mode, and it will operate depending on how much rotor power that you are injecting. Depending on that, the machine will operate as a generator at this point. Is that clear? Depending on, so how much rotor power that you are communicating, that means why communicating, you can either operate as a motor or as a generator depending on how much power that you are injecting to the rotor or taking from the rotor. Depending on that, the operating point on that characteristics curve will be decided. So, this can be done instead of this can be done using a back to back converter. Okay. This is a back to back converter. So, here the power flow is bidirectional. You can either extract power from the rotor or inject power to the rotor, and finally you can operate this as a generator. Okay. Now, as I told you, the voltage levels are different. So, what you can do is, depending on voltage matching, what you can do is you can use multi-level converters. Okay. Multi-level instead of 2-level converter, what you can use it, multi-level converter like 3-level NPC. Why I am saying 3-level NPC? Because 3-level NPC were invented, reported long back in around 1980s. Okay. But nowadays it is a state of art. NPC is a state of art and it is used. So, it is one of the versatile multi-level converter that we are using in the industry. So, this 3-level inverter we can use instead of 2-level inverter. Now, people, when I ask to my students in class, generally people say that we use multi-level converter because we get nice output, like stepped output from the, I will show you how it looks like. This is the multi-level output that you have in 3-level inverter. Okay. So, people say that in order to get this we use multi-level. No, we do not use to get multi-level output. Multi-level output is an advantageous outcome out of using multi-level converter. Okay. This is the advantage that you are going to get out of it, but this is not the desired thing that we are looking for. Means this is not the reason why we are using multi-level converter. The reason is, here you see the total desilting voltage is there, total desilting voltage is VDC. So, here this is half the desilting voltage. So, the voltage that this device has to withstand is half the desilting voltage. In order to reduce the voltage across the device, we use multi-level converter, because the maximum voltage withstand by whatever switches, power electronic switches available in the market, which is limited, but we have to go for higher power level. So, this kind of configuration we can introduce, so that low power devices can be used for high power applications, and the topology is completely changed. Because of this, with low power devices, high power application is feasible, and this is the outcome that we are going to get. Because of this, what is the advantage that we are going to get is, the output filter size is reducing. This is the another advantage that we are going to get from this thing. Okay. So, it is already a state of art, large voltage step. Now, we do not have large voltage step across the devices. Also, the voltage steps that is appearing across the machine is reducing. Okay. Because one of the major reason of machine failure is bearing current. Okay. That bearing current comes because of common mode current. That common mode current comes from common mode voltage. If you can reduce common mode voltage, definitely the failure of the bearing will be reduced. So, 3 output voltage levels. Okay. So, this is fine. Another thing is so like this. So, here what I mean to say is, so here back to back converter, what you can use it, you can use depending on this voltage level, what you can use is multi-level converter that you can use in order to cope up with the voltage level that we are increasing. Or one of the very popular multi-level converter that is very much now popular in HVDC application. Almost every HVDC application, every DC application is using this converter. It is a modular multi-level converter. Okay. You can see over internet, there are many companies in China and all over the world, they are preferring this converter and they are implementing. These are voltage source converters, voltage source converter, voltage source converter. So, this is back to back converter, back to back converter. Okay. So, 2 back to back converter also we can use. The advantage of using this is it is a modular in structure. So, each module looks like this. So, if there is a problem with one module, you just replace it, downtime reduces, which is very much required for industry, downtime reduction. Okay, scale up. If you want to increase the voltage level, you just add blocks, you add blocks and increase the voltage level. So, if you can come up with the, so the transformer-less operation is also possible because voltage level you can match. Okay. But the problem is definitely nothing comes free. The problem is structure becomes very complex now. Okay, control this capacitor voltage balancing, this capacitor voltage balancing, you need to have a different sorting algorithm you have to implement in order to make the capacitor voltages balanced. Okay, complex control. Okay. Now, this is not MMC output, this is one of the multi-level converter output. So, just I want to show you that as number of level is increasing. So, here number of voltage levels are increasing, so that this is phase voltage, this is line voltage. So, that current that we are generating, the filter requirement is reducing. So, multi-level converter if you use, it is voltage matching you are doing. At the same time what you are getting is, you are getting filter size reduction and other advantages that is coming up also you will have. Okay. So, back to back converter that we are going to use for this hydropower plant, either it could be rotor fed or it could be a stator fed, and this back to back converter you can have different configurations. So, conclusion is power converter play a major role in renewable energy extraction and integration. Without power electronic converter you cannot think of. And then converter topology depends on source and load requirement that I explained in very first slide. And then the two options that I told, the doubly fed induction machine and converter fed synchronous machine, these are the two options that we have. And back to back converter is the one of the popular solution, because if it is a definitely if it is a DC, if you have to connect to a DC grid, you connect a 3-phase AC to DC and then you subsequently use DC converters whether it is required or not. Multi-level converter topologies like NPC, MMC are preferred. Now, see why I just limit myself to NPC and MMC, because NPC is very stable, MMC is also very stable. Since MMC is suitable for HVDC, now MMC they are using for, there are papers where MMC they have used for motor drives application as well. Okay. So, these are the references. So, I have to stop here. Okay. So, any queries I can address from offline and online participants. Yes.
Hello.
Sir, in case of multi-level inverter, so when we increase the level, that means the harmonic content will be lesser, but as well as the power loss in the switching loss will be more. So, what will be the ideal level?
Now, switching loss in multi-level converter are less, because when it is multi-level converter, inherently you have to use switching frequency, the carrier frequency that we use for let us say 2-level converter, which is 10 to 20 kilohertz. Here we use much less, maybe 2 kilohertz, 1 kilohertz. So, switching losses are negligible. Yes, conduction losses we have to see, okay, that we have to compare. This many a time I face this question, like how to compare the efficiency. Efficiency comparison I am not happy with, because efficiency comparison you need exact same situation, exact same operating condition, and then you can compare the efficiency. So, commenting on efficiency whether it will increase, decrease, that is very hard to say. But I can say that switching losses in multi-level converter are much less, because you already have stepped output voltage waveform.
So, what is the ideal level that we should go for?
Now, ideal level will depend on what? It is not harmonic content, it depends on the voltage level.
Voltage level.
Yes,
yeah.
let us say the voltage level you are happy with 2 modules. Here in, let us say I take the example of MMC. If 2 module per phase you are able to achieve that voltage level, then use 2. With 2 whatever voltage level you are going to get, that is the voltage level. but if you want to increase voltage level, you have to increase this. So, this is the primary requirement, you have to match the voltage level, and with that whatever multi-level output you are getting, that is the advantage. Anyone else? I think somebody messaged. No? Okay. Because okay. Okay. Thank you then.
Yes. Okay. So, in this lesson we will look at types of hydropower turbines used in small hydropower projects. So, large hydropower projects usually have conventional types like Pelton and Francis, where we are going to look at, but there are other versions that are preferred in small hydropower projects. We will look at all possibilities. So, the function of the turbine is to convert the kinetic energy in water jet to kinetic energy in the turbine and impart it to the generator. So, the potential energy in the water at the high altitude will be converted to kinetic energy, and which will be imparted to the turbine, and then from the turbine shaft it will be transferred to the generator, and then the generator will be converting it to electricity, and that is the energy conversion part. So, there are many types of hydro turbines used in small hydropower plants. The type of the turbine for a particular project depends on the head and the rated flow of the project. So, which we now know how to determine. The expected turbine speed is also a consideration, because usually turbines work at lower speeds. So, the lower speed turbines is a problem, because then you need lower speed generators which are multipole. So, multipole turbines with salient pole type are expensive, and therefore, it is a consideration. Thus, different turbines are produced for high head, medium head and low head projects. Depending upon the way the water enters and imparts energy into the turbine, they are further categorized as impulse turbines and reaction turbines. Two major types of hydro turbines are impulse turbines and reaction turbines. So, in an impulse turbine, water jet hits the turbine bucket and passes away from the turbine. The runner of the turbine is inside a chamber containing air at atmospheric pressure. So, in an impulse turbine, there are number of impulse turbines, but the turbine runner is in air, right. It is not immersed in water. Therefore, water hits the blade and passes through and go to the tail race. Reaction time turbines are completely immersed in high pressure water. Then the water comes and pushes the rotor and goes away. The kinetic energy of the water is imparted to the turbine runner when water goes through the turbine blades as per the Bernoulli principle. I think you know the Bernoulli principle, where the aeroplanes also work, because one surface is longer, other surface is shorter. Therefore, when the fluid flow is there, there will be an additional force because of the vacuum effect. So, that the same principle is used in these reaction turbine blade configurations, so that the force can be created for the rotation. Impulse turbines such as Pelton, Turgo, cross flow and reaction turbines such as Francis, Kaplan are commonly used in small hydropower plants. So, we will now look at some characteristics of and the types of impulse turbines. Impulse turbines are very popular in small hydropower plants due to variety of reasons: ease and cost effectiveness in fabrication, less vulnerability to sand and other particles that may enter the turbine in operation, high part load efficiency are some of them. Pelton, turbo and cross flow are some of the famous impulse turbines used in small hydropower industry. So, you know that normally in any country or any region, when they start the construction or implementation of small hydropower projects, normally they start with high head project opportunities, because they are more cost effective, easier to construct, smaller in size, because the amount of water you have to handle is smaller, Q is small, H is large, high head projects, they are easier to implement. So, once you have exhausted with high head project, you will go to medium head projects, and then if once the medium head projects are also done, you will go to low head project. That is the normal sequence, normal sequence. But of course, there can be here and there differences because of the opportunities and other available situations, but this is a normal way. Therefore, impulse turbines and high head projects are normally preferred in small hydropower industry. So, Pelton turbine is the king of high head turbines. So, in large projects or small projects, Pelton is a very proven old technology and very efficient, and also the technology has been improved in construction of that. The runner of the Pelton turbine has a set of buckets connected to a steel wheel. The high pressure water coming through the nozzle in case of a single jet or several nozzles in case of multi-jet hits the turbine buckets and imparts the kinetic energy in water to the rotating kinetic energy in the turbine runner. You can see the typical turbine, Pelton turbine here, right. You can see the buckets. So, the water jet comes and hits this middle portion, middle ridge, right, and then water goes to the two sides and goes away, right, goes away. And this is that this construction is monolithic, that is this entire thing is cast in as a single piece, and then the blades are machined, right. Therefore, it is lot of machining and labor work, because you can't do completely by full machines here, right. People's intervention is required because of the complicated shape, and therefore, the balancing and identical these buckets have to be identical, and finally, the entire thing should be fully balanced. Otherwise, what will happen? Otherwise, vibrations will result in when it is rotated. Therefore, it is imperative that the full wheel is balanced, right. So, because of all these things, Pelton wheel is a bit expensive to build, and it has to be very sophisticated technology in machining process. There have been efforts to make these buckets separately, and then either to bolt or weld to the rim, right. But that has not been very successful, because of the that when the water hits bucket, full stress goes to the stem, right, and next moment it is released. Therefore, the bucket stem undergoes lot of stress and release, right. So, that causes failures, we will come to it again, right, when we see some more details here. Here you can see this is the nozzle that I talked about, needle valve I talked about in previously, right. So, this is the needle, this goes up and down, right, opening and closing the jet. So, when you want to reduce the generation, you just simply insert a little bit, so that the Q of the rate of flow rate of the jet will be reduced, right. So, that is how that in a run of river scheme, we will come to this later in a later discussion also. In a run of river scheme, water coming into the project can vary slowly during the day. If a rain comes, slowly the flow rate goes up, then the flow level at the or the water level at the forebay tank tries to go up, which will be sensed and the signal will be sent to the needle valve, open a little, right, open a little. Then again water consumption or the flow rate will increase and thereby the forebay tank water level will come down. We will discuss that in a different place in detail. Here you can see the water coming through the nozzle after hitting the buckets reflects back with an angle of 165 degrees to avoid interference with the incoming water jet, right. So, water comes here, goes out, right, with 165 degrees reflection and then goes out without hitting the incoming water jet, right, incoming water jet. So, you can see about 93% of energy is imparted, balance goes with the water, right, balance goes with the outgoing water. Right. Pelton turbines can be installed with its axis either vertically or horizontally. However, the horizontal axis Pelton turbines are more common in small hydropower plants, whereas the vertical axis configuration is common in large hydros. So, I told earlier also large hydros the weight of the generator and the turbine are excessive. Therefore, if you have horizontal axis might deflect due to the weight and therefore, it is a problem. Therefore, they prefer the vertical axis configuration with a thrust bearing at the bottom. Right. And here you can see the physically constructed nozzle. Right. Here the nozzle part you can see now this is fully closed. Right. This is fully closed. So, it has to be taken out. This is dismantled state. So, it is in the fully closed state. So, it will go back when you want to open the nozzle, right, open the nozzle. And the problem with the welding or bolting is the that fatigue failure, right, fatigue failure. I think you have heard about fatigue failure. When you take a steel wire and bend a couple of times, it breaks. That is due to the fatigue failure, right. Several times you bend it, it breaks. They are the same way when these buckets are subjected to constant regular stress at the bottom, at the stem here, right. So, it gets fatigue failures, right, fatigue failures. So, after some time cracks develop and when one bucket breaks, it can go around and hit the other buckets and destroy the entire system, entire wheel, Pelton wheel, right, if the one bucket breaks. So, it has happened. So, for very small, so I visited before buying equipment some Austrian companies and German companies, they make very small, maybe 50 kilowatt like small plants still with buckets separately made and welded or bolted. But for large machines above say 200 kilowatt and above, they always cast one piece and then carve or machine the buckets, right, machine the buckets separately. Here I think we discussed this as elsewhere as a answer to a question. Here are some typical efficiency curves of hydro turbines, right, efficiency curves. You can see the Pelton is having the very good part load efficiencies, right. So, this is the percentage Q, right, percentage. This is efficiency in percentage, right. So, you can see the Pelton turbines have very good efficiencies, right, very good efficiencies. For large hydro it can go even little above, and then you can see Kaplan has the second better efficiency. Kaplan machines we will discuss in a little while, and then the Francis, right, has some poor part load efficiency. If it is 30%, efficiency will be 70%, whereas in Francis it can be Pelton it is 80%, right, and other cross flow and propeller type machines, they have very poor part load efficiencies. I will come to this curve set again when we discuss about other types of Francis and other turbines, right. So, the Pelton turbines operate with a high efficiency over wide range of flow rates. Therefore, for power plants with a wide variation in the flow rates during the year, if other parameters permits, Pelton turbines are preferred. Pelton turbines are preferred to be manufactured from a single monolithic alloy steel casting. The buckets have to be carved into the casting and involves a challenging skill job. The involvement of machining is limited and work is labor intensive. To reduce the cost of manufacturing, efforts have been taken to manufacture buckets separately and either to bolt or weld them to the wheel. However, fatigue failures have been recorded in many such instances, and therefore, unless for very small turbines, monolithic construction is used. So, these things I explained earlier. So, Pelton wheels therefore are cast in single piece and then carved into the buckets are carved into it. The turbo turbine probably you may have not very much heard. So, it is a variant of Pelton, right. It is also impulse turbine. So, I have put a turbine here. So, if for one of our projects we used turbo turbines, this 2.5 megawatt machine power plant, we put 1.25 into 2 turbo machines, right. So, they have been working now last 20 years, no issues, right. That is, but these turbines are relatively little smaller for the same capacity and also cheaper. So, price was the main factor why we selected this turbine, turbo turbine, right. So, we can see here. So, this is where the water enters, right, and jet is here, and it goes from inside from this side and comes out from this side, this other side, right here, like here. So, the needle valve and that system is the same as Pelton, water jet and control, everything is same, but now how it enters the wheel is different. It enters from one side and goes out from other side, right, imparting energy. Like the Pelton turbine, turbo is also an impulse turbine. The technology was developed relatively late by a British manufacturer, but today there are several manufacturers of turbo turbines. In a turbo turbine, the water jet coming from a nozzle enters the turbine from one side and exits from the other. Therefore, there is no chance that the exit water hitting the incoming water yet, and therefore, there is no necessity to control the incoming water jet on this account. Right. So, these are advantages, but their efficiency is also run into the similar levels. You can see, not I think turbo turbine is not here. Turbo turbine is almost like Pelton turbine, right, almost like Pelton turbine. So, you can consider turbo, for turbo also the same efficiency curve. So, for the same capacity, the diameter of the turbo runner is smaller than the diameter of the same Pelton runner and therefore cheaper. Moreover, the turbo runner obtains faster rotating speeds and therefore easier to connect to a generator of the higher speed. Similar to the Pelton turbine, turbo also has good efficiency over wide range of flow rates. Therefore, for small hydro projects with wide flow variations throughout the year, turbo turbine is also a good application. Turbo turbines can also be installed with either the axis in horizontal or vertical position. Manufacturing of turbo turbines is more difficult compared to a Pelton turbine, and the buckets of a turbo turbine is more fragile. However, being smaller in size, turbo turbine is cheaper compared to a same size Pelton turbine. You can see this shape, you can see these are not very thick. Therefore, if something hits it, it will easily split, but not like Pelton is more sturdy looking. You can see the Pelton buckets are more stronger, right, but turbo buckets are more thinner, right, and can be damaged easily. So, therefore, we have to take care of any strange objects coming in and hitting the turbine. So, these are the hydraulic parts that are used to control there is a hydraulic unit here to control the needle valve, right, needle valve for the signals coming from the control room. And the cross flow is a third type of, this is again a impulse turbine, but simple construction. It is just a drum, right? It is just a drum, and even locally can be fabricated. You can see from this opening, water comes and hit the this runner, right. The runner of this impulse turbine has a shape of a drum. One or several runner portions comprising of number of blades fixed between the two discs are fixed on the same axle. The cross flow turbines are relatively always installed with horizontal axis. So, it is a simple construction, even we can locally manufacture, right, locally manufacture it. Here are the advantages of it. You can see water coming from a rectangular opening is uniformly spread over the turbine, but you can make sectionalize it here, like here you can see you can sectionalize the opening. When there is less water, maybe a portion of the runner is hit, right. When there is medium water, two sections are hit, and when they have full range, you can have full water. So, accordingly your efficiency curve will be operating, right. Therefore, you can again flat efficiency over wide range of part loads, right, part flow rates, whereas Francis does not have that. Francis have poor part load efficiencies. But you can see, notice that this the peak efficiency of this cross flow turbines will not reach 90 level, maybe 80, 85, in that range it will stop, right. The peak efficiency will be lower, but this is good because it can be even fabricated locally, not much higher technology is required. It is just you can see between two plates system of blades connected, right, and so it is just with this tail you can even weld them and make it even a local turbine. For a village hydro, I think this might be a better option, because you do not want to spend lot of money. Then we come to the reaction turbines, second type of turbines, right. So, they are the runner is completely immersed in water 100% of the time, right. The most popular reaction turbine is the Francis turbine, we all have heard about. They are more suitable for medium head projects. For smaller heads, the propeller type Kaplan turbines, right, are most suited. Reaction turbines have relatively higher rotational speeds compared to impulse turbines, and therefore, it is easier to avoid a gearbox between the turbine and the generator. The fabrication of reactive turbines are relatively more complicated due to special shapes associated with the runner blades of them. Here you can see some Francis turbines, how they operate. You can see here this the spiral case going around. So, the water enters from this large entry, and then from periphery they enter the turbine runner, right. So, there we have we do not have nozzles like needle valves, we have what we call the wicket gates, right, wicket gates, that side wicket gates which can which can open, right, and then there are guide vanes to guide the water flow and smoothly enter the turbine blade. The turbine blade operates on the principle of the Bernoulli principle, where you have one side longer, other side shorter. So, the flow comes here just like the air flow through a aeroplane. So, they have to leave the same way. Therefore, this side the speed is, they have to go faster, this side slower. Then there is a vacuum effect here, right, vacuum effect here. So, it will be lifted, right, or on this side there will be a force, right, there will be a force on this side. So, the blades have been shaped in this way, right, blades have been shaped in this way. So, when the flow goes on one side, there will be a force for the rotation, right, force for the rotation. So, the turbines of Francis turbine is enclosed in a spiral casing and the high pressure water is encircling it. wicket gates release the high pressure water under controlled conditions to the turbine runner, while the guide vanes assist to enter the water to the correct angle. Water flowing through the complex shaped runner blades imparts the energy to the runner while exiting the turbine axially. So, finally, the water will be going down from the middle to the tail race. Right. Here we can see the hydraulic control of the wicket gates. So, there are, you can see this will be rotating these brackets which are connected to the wicket gates inside. So, when you want to open and close, this will be going up and down, right, and the hydraulic pressure will come as per the signals coming from the water level controller or from the the control system in the power plant. Right. So, there is a that way that we can overcome this problem of part load poor efficiency of Francis turbines, right, Francis turbines, by employing, if you have a site, say you have a site where you want to have 1 megawatt or 1000 kilowatt plant, where Francis turbine is the suitable machine, but you have part load deficient, part load lot of time to operate part load, because if you look at your flow duration curve, right, Q percentage time or exceedance, right, it is like this, right. So, lot of time it will be in operating in low flow conditions, your rated flow may be here, right. There are lot of time machines are on part load, machines are on part loads. Therefore, you are operating here these efficiency points, right, which is a disadvantage, So, one solution is, instead of putting 1000 kilowatt machine, you put a say 700 kilowatt machine plus a 300 kilowatt machine, right. So, in the low flow conditions, you run the 300 kilowatt machine, which can run on almost full rated flow, because that small flow available will be the rated flow of this 300 kilowatt plant or the turbine, right. So, when you have medium flow, you use only the 700 kilowatt one. When you have high flow condition, somewhere here, you use both. In this region, you use 700 kilowatt, here you use 300 kilowatt, right. So, that your machines will operate always in the higher efficiency points, right, higher efficiency points. So, I visited one such plant in Germany. Here you can see I do not have both the machines here, this is the larger machine, there is a smaller machine here, right, from the same power plant. I could take, I do not have a picture with both clearly here, right. One machine is a large one and the other one machine is a smaller one, right. So, this is feeding to a factory, right, this is feeding power to factory. So, they have used these different sizes because of the efficiency considerations, right, because of the efficiency consideration. So, one might ask then that you can't exchange spare parts etc., right, from one machine to the other, but these technologies are very proven. So, anything going wrong with the turbine is a very low chance, even the generator technologies are very improved now. Therefore, unless you get a lightning strike or something and you destroy it due to your own mistakes, otherwise they are so reliable, no, you do not need to keep spare parts, it will happen very rarely, right. These are very proven technologies. Of course, your relay systems and other things can fail, but the generator, turbine etc., will not easily get damaged unless you make a mistake in your management or protection. Therefore, having two sizes is not a problem. Therefore, you can always advise, if some people are going for Francis turbines, consider having two different sizes, right, two different sizes. People prefer to put the same size. If you want to put this 1000 kilowatt, they might say then 500 into 2, right, and to go for similar capacity, that is the normal pattern. but in this hydropower business we have to consider the efficiency curve, right, efficiency curve and suitably. And also then some might ask the question, how did you decide this whether it is here you have a picture, here you can see this is a smaller turbine, this is a bigger turbine, right. So, a smaller one runs when the flow is low, other one runs when the flow is high, right. So, one of the disadvantages of Francis turbine is that at part load the efficiency drops very fast. As a solution to this problem, the hydropower engineers sometimes opt to install one large Francis turbine together with a relatively smaller turbine at the same plant. Smaller turbine is used during the low flow conditions, and when medium flow is available, the larger unit is used. When the available flow rate is maximum, both turbines operate, right. So, you should be able to advise, right, anybody doing a Francis power plant, consider this option, right. Then how do you decide whether it should be 1000 kilowatt or 500 into 2 or 700 plus 300 or maybe 800 plus 200, right. So, we may have to decide, right. So, how do we do is we do an energy generation calculation for each configuration, which we are going to see at a later discussion, right. We are interested in to see how many kilowatt hours or megawatt hours a plant can deliver, that we will discuss in a different program, right. But here you can see, so we must see what is the cost of the plant as well as how many million units kilowatt hours you can produce in this configuration, how many kilowatt hours, here how many kilowatt hours, here how many kilowatt hours, if you have the different configurations. So, because of the higher efficiency, highest efficiency one will produce the highest energy yield, right. And then you have to consider the cost also, because if you have one machine, your control system is only one control system, one synchronizing breaker, and the powerhouse will be smaller. But when you have two machines, little more space is required and the two control systems are required. So, some additional cost will be there. Then you must see whether the increase in the power generation is worth the additional cost over the long term, right. That financial analysis also you have to do, right, because otherwise you just for a few kilowatt hours, if you duplicate your everything, control systems and synchronizing and all the control panels, then it might be not that worth. So, after doing the calculations only you should decide which configuration and which capacities, right, which capacities to be used. Here this of course, this plant was feeding a hydropower turbine manufacturing plant. They have opted for, they have a hydropower opportunity in that area. So, they have their factory is fed by hydropower, right. They have a grid connection, but mostly they use their own generation, right, mostly they use their own generation. So, they have opted for the vertical axis, this is vertical axis configuration, right, in both units are in vertical axis configuration. Here's a Kaplan turbine. Kaplan turbine, has a it's a propeller. Propeller, you have heard the word, I think. Propeller is the driving unit of a ship, right, a boat. I think you have seen the boats propellers, right. So, people take it out and go and fix it back, right, when they want to go. So, but in a ship it is permanently there. So, it is a propeller, when rotated pushes the ship forward, right. And so, this is the same technology. Now, the propeller is fixed and the water is pushed to it, then it begins to rotate, right, then it begins to rotate. But Kaplan is in an improvement of normal propeller, right, normal propeller, because in Kaplan the blades can be adjusted, blade angle can be adjusted to suit the better efficiency and to increase the efficiency for the given flow, right. So, the Kaplan is just a propeller turbine, where the blades can be adjusted by hydraulic means to maximize the efficiency, right. So, the design similar to a propeller of a ship, Kaplan turbines are very famous for low and ultra low head projects, Propeller type turbines are connected to the penstock, so that the axle of the turbine can come out of the pipe and can be connected to a generator, right. So, it is normally comes out of the pipe, the penstock. One marked advantage of Kaplan turbine is that the pitch of the blades of the turbine can be adjusted according to flow and thereby achieve higher efficiencies. So, here are some some parts of a typical project. You can see the same way wicket gates are there, guide vanes are there, the water comes and enter here, go through the blades and pass on to the other side, right, pass on to the other side, that is the normal way, and there while passing the same thing, same Bernoulli principle, shape of the blades will be having the similar pattern. So, that there is a longer path and a shorter path, thereby creating a vacuum and a force and thereby rotating it, right, rotating it. So, they are more suitable for low head projects and ultra low head projects. So, in one of our power plants we installed Kaplan turbines in a which is connected to a reservoir. So, because there was a irrigation outlet, as we discussed about some configurations earlier, there was a reservoir in Sri Lanka in middle part of the country, and where they issue water for irrigation work and for drinking purposes, and there is a height difference between the water issuing point and the water flow, about 30 meters. So, we discussed with the government authorities and got the approval and installed a 2.5 megawatt power plant there with two turbines, right. And so, they are Kaplan turbines. Now, they have been operating in last 10 years, no issues. Of course, we had one issue, as I told you earlier, that the penstock is FRP pipes, fiber reinforced plastic pipe. So, because of that vehicle movements, those got damaged by the pressure. So, we had to replace them. Other than that, about Kaplan turbine, there have been no issues. You know that your home water pump can also be used as a generator, a turbine, right. Home water pump, now when you rotate it, it will pump water up, right. But if you send water through it, it will rotate, right. So, if you want to, now if you have a in your home in a hilly area, if there is a waterway, you can easily put a pump, right, water pump as a generator and connect it to a induction generator or something very cheaply and generate some electricity. But the problem is their efficiency will be 50%, not that high, right, because they are not designed as hydropower turbines. But of course, as a practical means, they can be very easily used as a practical machine to produce electricity, but they are not very efficient, right. By sending water in the reverse direction, centrifugal pumps can be used as turbines. However, one of the main disadvantages of these pump turbines is that the efficiencies are very low. It is very rare that pumps are used as turbines in building small hydropower plants. Main advantage of these turbines, they are available off the shelf, right, and pretty cheap as well. You know, one problem with the hydropower turbines is, whatever Francis or Kaplan or Pelton or whatever, right, these turbines you can't use any second hand turbines for a site, right. Second hand turbines you can't get. Why? There are no two identical, theoretically there cannot be two identical power plants in the world, right. No, in no power plant theoretically H and Q can be the same, right. H and Q cannot be the same in any two power plants. So, H is depends upon the height difference available, Q depends upon your catchment area and other things. So, it is hardly possible in two power plants both are the same. Therefore, these turbines have to be manufactured especially designed for this H and Q, right. So, you can't ask a hydropower turbine manufacturer, can you manufacture it in 2 months? He cannot. He has to first do a design and then manufacture it. So, they will take 6 to 9, 10 months for the manufacturing process, right, and then the generator also has to match the speed, right, number of poles, etc. So, it is a salient pole generator manufactured especially for this particular turbine speed, right. Therefore, they all take time to manufacture, right, they all take time to manufacture. Therefore, they are not available off the shelf, right. You can't go to a shop and buy turbines or generators for hydropower plants. So, they have to be specially designed and manufactured for the given site, right, for the given site. And also there are issues like that even though we say this efficiency, now manufacturer will say efficiency curve is this, right, but it is very difficult to measure this at the site, right, at site for the verification how to measure these efficiencies is very complicated. Therefore, you can't now manufacturer will, even if he claims his machines are having 90% efficiency, to test it and confirm it at site is very difficult. Only possibility is if you are challenging him and asking him to prove it, he will say I will make a prototype and measure the efficiency in lab scale for the prototype. That is the best he can do, right. Measuring is not impossible, but it is a time consuming and lot of money is required for various parameters to be controlled. So, I have not seen any site where they confirm the efficiency curve by tests. It is a very lengthy process, right. It is a very lengthy process. So, not worth doing. So, that is why we have to take a good reputed manufacturer, right, get reputed manufacturer when you buy hydropower turbines. Here I think we discussed earlier, right. So, for all the turbines, so you use a turbine application chart for selection of the turbine to suit your head and flow rate, right. So, therefore, your particular plant can be any point in this chart. So, theoretically no two plants can be at the same point, right. Okay, accidentally it can happen, but theoretically we can't say any plant can be having the same location in this turbine selection chart, but you have the same multi options. If you are here, you have the option for going for Pelton or Francis both, right. Then you can take a decision depending upon your flow. If your flow is like this, then your low flow conditions are less, low flow conditions you can see, but mostly your flow is high flows, right. Then in that case you can use even a Francis machine, right. But if it is like this, right, it is different, right. You have lot of part load conditions. Therefore, you must consider a Pelton machine, right. Therefore, when you have multi machine options available, you must look at the shape of the flow duration curve, right, flow duration curve. Now, why the flow duration curve have these shapes? Now, when you look at the flow duration curve, you can tell the properties of your catchment area, right. When I look at, if somebody shows me this curve as his flow duration curve, I notice his catchment has less forest, right, and more rocky. What does it mean? The rain comes, water is quickly rushing into the river and going out, right. Therefore, high flows are more for a short time, right, and then water retention is not there. So, this is not good, therefore, this is not a good flow duration curve. This is a good one because water is retained in the forest or whatever the cover, vegetation cover, and slowly released over the years, then you can utilize it more, right. So, you can tell the properties of the catchment area by looking at the flow duration curve without visiting even the site. So, most of the surfaces are this one, most of the surfaces are rocky and less water retention, right. So, these are important things that when you are looking at the project. So, we discussed here the types of turbines used in small hydropower and special versions like turgo. Turgo is not used in large hydros, they are especially for small hydros, and Pelton is very much used in both small hydros as well as both Pelton and Francis are famous for the entire range from small hydros to large hydros. And so, the turbine selection should be carefully done, and when you are using multiple turbines, right, multiple turbines, you can consider having different sizes if the part load deficiencies are poor of that turbine. So, that you can run the smaller version when the flows are low and the bigger version when the flows are medium, and both turbines when the high flow rates are available. I think we will stop there this discussion, and if there are any queries I can take up. From the online people and physically here.
Hello, sir.
Yes,
this
please.
is Supriya.
Yes, Supriya.
Sir, how these hydro turbines are different from the other turbines like gas turbines or other input turbines like nuclear turbines? Any change or?
Yeah, gas turbines. So, in the gas turbines you can see it is a hot in the hot air or heated air that passes through the turbine. You can see, and the construction wise there are large number of blades in a different shape, right, in a gas turbine what I have seen, and it is not a liquid that is flowing, it is a hot air. Hot means the heated air with energy goes through it, but after fuel burning or the gas burning goes to them and impart the energy into them. So, those blades are operating at very high temperatures. So, their construction, their materials, I am not an expert on gas turbines, but what I have seen is they operate in a completely different environment, and they also usually comes in two compartments, that is high pressure turbine and the low pressure turbine connected to a same shaft. So, first the hot air goes to the high pressure turbine, and then it passes go into a low pressure turbine, and their turbine blades are different, and thereby they try to maximize the energy usage, right. But in hydro turbines it is not like that. Hydro turbines, it is the fluid that goes through, of course, air can also be considered as a fluid in a way when it is flowing, but the hydro turbines, it is a physical impact by a impulse turbine or reaction by the fluid on the say Francis turbine, but a similar action is taking place in air flow in a gas turbine also, but the conditions are different. It is a heated hot chamber, this is a water chamber, but I think the operating principle may be the same as the Bernoulli principle in both cases.
Yes, okay, sir.
Okay.
Thank you, sir.
Okay, thank you. Any other questions? Okay, we wind up there. Thank you.